A telescope on Mauna Kea locks onto the exact center of the Milky Way, 26,000 light-years deep into Sagittarius. It's May 13, 2019, and the astronomers aren't expecting anything. They've been watching the same black hole for years, and it barely flickers. Then at 10:47 p.m. Hawaii time, the infrared flux monitor spikes, hard. The software flags the reading, then flags it again. Two researchers lean into the same screen, watching the brightness curve climb in real time, and nobody says a word. Sagittarius A. The 4 million solar mass anchor at the core of our galaxy is suddenly glowing, not a little, not a calibration drift. The signal is violent, sustained, and completely unexplained. The number on the screen was so far outside normal that the first thing they did was assume their own telescope was broken. They checked the optics, they checked the atmospheric correction, they pulled archived data from 13 years of prior observations. The black hole had never done this. That night, the brightness spiked to 75 times the median flux recorded between 2006 and 2019. Not 75% brighter, 75 times. For perspective, that's the difference between a candle and a floodlight. The flare lasted roughly 2 hours before fading back toward baseline, but the damage to every model was already done. Sagittarius A had been the poster child for a dormant supermassive black hole, the kind that sits in the dark and barely feeds. This was supposed to be the calmest sleeping monster in the sky, which is exactly why the flash was so wrong. Most galactic centers scream. Quasars pump out more light than 1 trillion stars. Active nuclei blast jets of plasma thousands of light-years into space. Ours does none of that. Sagittarius A accretes maybe 1 Earth mass of material per year, a starvation diet for something that massive. Its luminosity sits roughly 1 billion times below what the physics allows. It's so faint that for decades we couldn't even confirm it was there. That quiet let us map the orbits of stars around it, measure its mass to within 1%, and treat it like a laboratory specimen, predictable, safe, in the way a caged apex predator feels safe. So when a second team pulled up their own recordings from that same window, the story stopped being a fluke. Within 48 hours, the emails started piling up. A Chilean observatory, a team in Hawaii, the European Southern Observatory's archive. All of them had caught the same surge, all within the same 4-hour window, all pointing at the same coordinates. Instrument error doesn't synchronize across hemispheres. It doesn't show up in independent datasets collected by telescopes that never talk to each other. The flare was real, and it had happened everywhere at once. What started as a curiosity turned into something else when the raw numbers came back. The brightness spike wasn't just unusual, it was 75 times the baseline, bright enough that if you'd been watching in the right wavelength, you'd have seen the galactic center glow like someone flipped a switch. And then a graduate student, overlaying the light curves, noticed a rhythm hiding inside the noise that no one wanted to explain. The rhythm wasn't random scatter. It pulsed, faded, pulsed again over 30 minutes, like something breathing. That pattern doesn't appear in background radiation or sensor noise. It appears when matter is moving, accelerating, heating up as it spirals somewhere it shouldn't be able to escape. For 20 years, the black hole at the center of our galaxy had barely flickered. It consumed almost nothing, radiated almost nothing, sat dormant while galaxies billions of light-years away screamed across every detector we pointed at them. And now, without warning, it woke up. The models didn't predict this. The stability calculations said we had millions of years before anything interesting happened. But the data didn't care about the models, and the brightness curve kept climbing in ways that suggested something had changed, something fundamental, something feeding. To understand why a handful of astronomers barely slept that week, you have to know what this object usually eats, and it is almost nothing. The questions hit all at once. If the black hole was stable for decades, what crossed the event horizon that day? If it's been starving for centuries, why did the feeding pattern suddenly shift? And if this was a one-time event, why did 3 smaller flares show up in archival data from the previous year that no one had flagged? Every answer opened 2 more problems. The accretion disk should have shown pre-flare heating. It didn't. The X-ray signature should have matched known patterns from stellar mass black holes. It didn't. The duration was too short for a star being torn apart, too long for a rogue gas cloud, too bright for background fluctuation. Some teams floated the idea of a collision, others a magnetic reconnection event. A few whispered about instabilities in space-time itself near the event horizon. But none of the math closed cleanly, and the more data that arrived, the less any single explanation held. But before any of it makes sense, we have to rewind, all the way back to a time before anyone knew this thing existed at all. So we're going back, not to last week or last year, but to the origin of the entire puzzle, to a time when no one had even heard the name of the object that would one day blaze across our instruments. We'll return to that flare, to the scramble and the confusion and the theories that don't quite fit. But first, you need to understand what we're actually looking at, where it sits, and why it took so long to find. Because the story doesn't start with the explosion, it starts with silence, with decades of patient observation, with astronomers piecing together a mystery from shadows and math and the slow waltz of distant stars. The light that startled those astronomers had been traveling toward Earth for longer than our entire recorded history. When the event happened, humans hadn't invented writing yet. We were still painting on cave walls, tracking seasons by the moon, telling stories around fires about shapes we saw in the sky. The photons raced outward through the vacuum, crossing unimaginable stretches of empty space, while empires rose and fell on Earth, while we learned to farm and build cities, and eventually to ask what those pinpricks of light above us actually were. By the time Galileo pointed his telescope up, the light was already more than halfway here. When Einstein published his field equations, it had covered 99.98% of the journey. That distance is the first clue, because it means everything we're about to watch already ended 26,000 years ago. 26,000 light-years, that's the radius of our vantage point, the span between us and the center of the Milky Way, where this thing lives. Every image, every spike in X-rays, every flicker we detect, is a postcard from the deep past. When we watch it flare, we're not seeing what's happening now. We're seeing what happened when woolly mammoths still walked the Earth. There's no way to know what state it's in at this exact moment. The light carrying that information won't arrive for another 26,000 years. We're always watching an echo, a ghost, a film reel that finished playing millennia before we were born. Most people never learn that for centuries astronomers didn't even suspect a monster was hiding behind all that dust. So here's what we know. A black hole, 26,000 light-years away, flared 75 times brighter than normal, stayed bright for hours, then went silent again. The flare happened in real time, not in some ancient cosmic past, which means the black hole's behavior is changing now. And if something that massive can wake up after millennia of sleep, the natural question isn't whether it matters. The question is what else it's doing that we can't see yet. What other signals are traveling toward us through the dark, carrying news we won't understand until they arrive? To answer that, you have to go back. Before the flare, before the satellites, before anyone knew there was a black hole at all. Before the center of our own galaxy was just a bright smudge in the sky, and the idea of a monster hiding there sounded absurd. It starts with a smudge of light nobody could explain, and a suspicion that felt like science fiction. Look south on a summer night and you'll find Sagittarius, the Archer, low on the horizon. Inside that constellation sits the densest part of the Milky Way's visible band, a hazy glow made of billions of stars packed so tightly their light blurs together. Early astronomers called it the galactic bulge. But most of what's there you can't see. Clouds of gas and dust, 25,000 light-years deep, block almost all visible light from the core. It's like trying to study a spotlight through a brick wall. Radio waves and infrared slip through, but for centuries, astronomers mapped the galaxy's heart blind, guided only by indirect clues. What they found was chaos. Millions of stars orbiting something, their motions synchronized like dancers circling an invisible partner. The closer to the center you looked, the faster those stars moved and the tighter they packed. The brightest region, a fuzzy patch catalogers named Sagittarius A, sat exactly where the orbits converged. Buried in that glow was a single point that behaved unlike any star ever catalogued. In the 1960s and 70s, a handful of physicists started suggesting something strange. Galaxies, they argued, might not just be loose collections of stars. Each one could have a gravitational anchor at its core, a mass so large it held billions of suns in orbit but emitted no light of its own. The idea wasn't popular. Black holes were still theoretical, equations on paper with no observed examples. Claiming that every galaxy hid one at its center felt like wild speculation, the kind of thing serious astronomers dismissed over coffee. But the math kept working, and the orbital speeds kept refusing to make sense without something massive and invisible pulling at their centers. A few radio telescopes started pointing at Sagittarius A anyway, half expecting nothing. What they needed was evidence, something concrete that couldn't be explained by a dense star cluster or a trick of the dust. The proof, when it came, arrived not as an image, but as a faint, stubborn crackle of radio static. In 1974, astronomers at the Green Bank Observatory in West Virginia locked onto a radio source barely 20 arcseconds wide, pinned right at the galactic center. It wasn't a flicker or a burst. It was steady, compact, insanely bright for its size. Follow-up observations with the Very Large Array in New Mexico confirmed it. The signal came from a region smaller than Mercury's orbit, yet it was pumping out more radio energy than entire star systems. Nothing that small and that bright had any business existing unless something extreme was holding it together. The spectrum looked thermal at first, then synchrotron. Electrons were spiraling through magnetic fields at relativistic speeds, radiating as they whipped around some invisible anchor. Whatever sat at the center was warping space hard enough to trap charged particles in tight, furious orbits. That crackle needed a name, and the name it got hid a small joke that stuck for good. Robert Brown and Bruce Ballack coined the designation in 1974. They'd been cataloging radio sources in Sagittarius, labeling them alphabetically. Sagittarius A was the brightest, sitting right at the galactic nucleus. Then they realized Sagittarius A had substructure. There was a diffuse cloud, Sagittarius A east and west, and then this weird, unresolved pinpoint in the middle. They needed a way to flag it as special, something exciting, worth a second look. So they added an asterisk. Sagittarius A star, written Sagittarius A. The asterisk meant exciting in astronomical shorthand, a typographic wink that this wasn't just another catalog entry, it was a placeholder for something no one had seen before. Naming it was easy. Proving what it actually was would take a 30-year stakeout of the stars around it. You can't weigh a black hole directly because it doesn't emit light, but you can weigh it by watching what orbits it. Stars near Scare A should move like planets around the Sun, their speeds and trajectories encoding the mass of whatever holds them captive. The problem was resolution. The galactic center sits 26,000 light-years away, and the region of interest spans only a few light weeks. From Earth, that's like trying to watch a firefly orbit a marble in Tokyo. You need adaptive optics to cancel atmospheric blur, infrared to see through the dust, and patience to track stars across years. If the stars moved fast, really fast, like thousands of kilometers per second, then the invisible mass had to be millions of solar masses crammed into a volume smaller than our solar system. No star cluster could stay that dense without collapsing. Only one object fit the math. So two rival teams pointed the biggest telescopes on Earth at a tiny patch of sky and simply waited. The campaign started in 1992. Andrea Ghez at UCLA and Reinhard Genzel in Germany both began tracking the same patch of sky, night after night, year after year. They were hunting for motion, tiny shifts in position that would reveal how fast things were moving near the center. At first, the stars looked like a frozen snapshot, but after 2 years, then 5, the dots started to drift. They weren't standing still, they were orbiting something, carving paths through space like planets around a sun. The rivalry was quiet but fierce. Both teams published updates, each trying to pin down the orbits with more precision. Ghez used adaptive optics at Keck Observatory in Hawaii. Genzel worked with the Very Large Telescope in Chile. The data piled up, season after season. By the late 1990s, they had tracked dozens of stars. The orbits were getting clearer, the speeds measurable. One of those stars was about to do something that would settle the argument forever. The stars weren't drifting slowly, they were whipping around an invisible point, some completing full orbits in just 16 years. That's fast. Our Sun takes 230 million years to orbit the galaxy once. The closer a star got to the center, the faster it moved. S14 was clocked at 8,000 kilometers per second. S4 hit 10,000. These weren't gentle curves. They were tight, violent ellipses, the kind you only see when something incredibly dense is pulling from the middle. The teams plotted the paths frame by frame. The orbits looped and crossed, all focused on the same empty point in space. Whatever was there, it wasn't glowing, it wasn't radiating, it was just bending space-time hard enough to fling stars around like marbles. The fastest of them, a star called S2, was screaming toward its closest approach, and everyone was watching. The reality was not that great. S2's orbit is a long, stretched ellipse. It spends most of its 16-year loop far from the center, moving at a leisurely few hundred kilometers per second. But then it dives inward, accelerating as it falls toward the invisible mass. In 2002, S2 reached periapsis, its closest approach. It came within 17 light-hours of the radio source, about 120 times the Earth-Sun distance. At that point, it was moving at 7,650 kilometers per second. That's 2.5% the speed of light. Both teams had infrared cameras locked on it the entire time. They measured the Doppler shift in its light, tracked its position down to milliarc seconds. The data was clean. The orbit was solved. The mass at the center could now be calculated directly from Kepler's laws. At that closest pass, S2 was moving fast enough to prove something no one wanted to be the first to say out loud. The math was simple. The orbit was tight, the speed was known, and Kepler's third law gave the answer without ambiguity. The invisible object at the center weighed 4 million times the mass of our Sun. That much mass packed into a region smaller than Mercury's orbit left exactly one option. No star could hold itself together at that density. No cluster of dead stars could stay bound without radiating signals we'd have seen decades earlier. A supermassive black hole was the only structure in known physics that could exist in that configuration. The event horizon would measure about 24 million kilometers across, dwarfing any star in the system, but fitting comfortably inside the space S2 carved out every 16 years. The conclusion wasn't speculative. It was measured, reproducible, and backed by 2 decades of precision tracking. That single conclusion would eventually stand on a stage in Stockholm. On October 6, 2020, the Royal Swedish Academy of Sciences awarded the Nobel Prize in Physics for the discovery of Sagittarius A. Reinhard Genzel and Andrea Ghez shared half the prize for leading the teams that mapped the stellar orbits and confirmed the supermassive black hole at the Milky Way's core. The award recognized 28 years of patient observation, technical breakthroughs in adaptive optics, and the coordination of observatories on opposite sides of the planet. It was proof that you could find a black hole not by seeing it, but by watching what it holds. The discovery had transformed our understanding of galactic structure. Nearly every large galaxy surveyed after 2002 was found to harbor a supermassive black hole at its center, masses ranging from millions to billions of solar masses, each one shaping the evolution of stars around it. But beneath the celebration, a tension lingered in the data. Sagittarius A was confirmed, massive and undeniable. It was also far quieter than it should have been. Even as the medals were handed out, one detail about how little the black hole was eating didn't add up. Supermassive black holes in other galaxies blaze. They gulp down gas and stars, heating infalling matter to millions of degrees and spraying radiation across the electromagnetic spectrum. M87's black hole, 2,000 times more massive than ours, shines so brightly it can be seen 53 million light-years away. Sagittarius A barely whispers. Its luminosity is roughly 1/1000th what you'd expect from a black hole that size, surrounded by that much available gas. It's accreting matter at a rate measured in thousandths of an Earth mass per year, sipping instead of feasting. The X-ray emissions are faint. The radio signal is steady but weak. There's no jet, no outburst, no sign of the violent feeding frenzies seen in active galactic nuclei across the universe. For a 4 million solar mass object sitting in a dense stellar neighborhood, it's eerily well-mannered. Theorists proposed starvation scenarios, inefficient accretion, magnetic field structures that choke the inflow before it reaches the horizon. The models worked on paper, but they required the black hole to sit in a delicate balance that shouldn't hold for millions of years. A monster that barely eats is either well-behaved or waiting, and no one could say which. Compare Sagittarius A to a quasar, one of those cosmic lighthouses screaming across billions of light-years, and you'd think we were looking at different species. Quasars pump out more energy in a second than our sun will produce in its entire lifetime. They're black holes gorging on rivers of gas, their accretion disks blazing so bright they outshine entire galaxies. Our black hole gets maybe 0.0001% of that diet. The gas around it is hot and diffuse, spiraling inward so slowly that most of it never crosses the event horizon at all. Magnetic turbulence scatters it. Winds push it back out. The feeding flow chokes itself before the meal arrives. Some supermassive black holes are feasting, ours is fasting, and the equilibrium looked stable, locked in by the sparse environment of our galactic center, by the geometry of the magnetic fields threading the inflowing plasma. A 4 million solar mass object barely glowing, barely moving, barely there, which is exactly why the faint whisper of light it does give off became the most watched signal in the galaxy. That whisper comes from the innermost stable orbit, the last carousel before the fall. Gas heats to 10 million degrees Fahrenheit as it compresses and shears, radiating in X-rays and radio waves. It's not much, a flicker you'd need a stadium-sized dish to detect, but it's constant, a baseline hum. Astronomers monitor it in shifts, logging every spike, every dip, every fractional change in brightness or spectrum. They're watching for turbulence, for clumps of matter arriving, for magnetic reconnection events that might brighten the glow for a few hours. The data streams in from Chandra, from the Very Large Array, from ALMA's 66 antennas in the Atacama Desert. The signal is faint enough that a supernova halfway across the galaxy would drown it out. But it's also predictable, cycling gently as the hot gas orbits and radiates. That predictability made it a laboratory. You could test relativity, measure spin, probe the magnetic field structure, all from the steady whisper of photons escaping the edge. To truly see the edge of it, though, humanity would have to build a telescope the size of the entire planet. The Event Horizon Telescope isn't one instrument. It's 8 radio observatories scattered from Hawaii to Antarctica, synchronized to atomic clocks, recording the same target at the same moment in April 2017. The technique is called Very long baseline interferometry. Combine the data correctly and the resolution jumps to 20 microarc seconds, sharp enough to read a newspaper in New York from a cafe in Paris. They pointed it at Sagittarius A. 5 petabytes of data, shipped on physical hard drives because the internet couldn't handle the load. Algorithms spent 2 years cross-correlating signals, stitching together fragments of wavefront, filtering out noise from Earth's atmosphere, from antenna jitter, from the interstellar medium itself. The goal was simple: photograph the shadow. Not the black hole, you can't photograph darkness, but the photon sphere casts a silhouette against the glowing accretion disk, a ring of bent light wrapped around an absence. Theory predicted the size, the shape, the brightness. The team worked blind, testing their pipelines on synthetic data so no one could bias the result. It took years of computing to develop, and when the picture finally resolved, the room went silent. There it was, a perfect circle of golden light, glowing against the void, wrapped around a disk of absolute darkness. The Event Horizon Telescope had captured something no human had ever seen: the silhouette of Sagittarius A. Framed by light bent so hard it curved 180 degrees around the edge. The ring measured 52 microarc seconds across, exactly what general relativity said it should be for 4 million solar masses sitting 26,000 light-years away. The brightness peaked on one side, where gas swirled toward us at nearly light speed. Doppler shifted into brilliance. On the opposite edge it dimmed, matter rushing away, redshifted toward invisibility. 8 telescopes, scattered across 4 continents, had synthesized into a single Earth-sized lens, capturing radio light at 1.3 millimeters wavelength with precision measured in billionths of a degree. The data had been flown on hard drives because the files were too massive to transmit, petabytes of recorded sky waiting to be aligned frame by frame. And when those frames stacked together, astronomers saw the ring flicker and shift, its brightest spots wandering clockwise around the shadow's edge. That ring was beautiful, but the way it shimmered from image to image hinted the thing was anything but still. The dark center isn't the black hole itself, it's the photon sphere, a region where gravity bends light into closed orbits, trapping photons that spiral inward or escape at wild angles. Any light emitted inside that boundary never reaches us, so we see a shadow roughly 2.6 times wider than the event horizon itself. The glow comes from the accretion disk, superheated gas spiraling inward at a fraction of light speed, friction tearing electrons from atoms and radiating across the spectrum. Some of that light shoots straight at us. Some curves around the back of the black hole, bent by spacetime into our line of sight, creating a secondary ring stacked behind the first. This is gravitational lensing pushed to its limit. Photons launched perpendicular to our view wrap halfway around the black hole and arrive from the opposite side, their paths twisted into horseshoes and loops. The resulting image is a superposition, light from the near side and far side and top and bottom all compressed into a single glowing halo. The shape of that shadow secretly encoded how fast the monster was turning. Every black hole spins. When a star collapses, its rotation amplifies, angular momentum conserved as the core shrinks to a point. The faster it spins, the more it drags space-time around it, a phenomenon called frame dragging that twists the orbits of anything nearby. Sagittarius A. Spin parameter came in around 0.9, where 0 is no rotation and 1 is the theoretical maximum. That's fast, fast enough to warp the inner edge of the accretion disk, tilting it, stretching the photon ring into a slightly flattened oval. Fast enough that the dragging effect reaches out 6 times the event horizon's radius, pulling gas into orbits that precess and wobble. The S-stars orbiting farther out showed hints of it too, tiny perturbations in their ellipses that matched the predictions for a rotating spacetime. The EHT images and decades of orbital tracking converged on the same answer. This wasn't a static well in spacetime, but a whirlpool, 4 million solar masses spinning once every few hours, churning the fabric of reality around it. And that spin axis, derived from the asymmetry in the ring's brightness and the tilt of the inner disk, didn't line up with the galactic plane. But spin alone wasn't the unsettling part. It was the direction that axis happened to point. The ring wasn't just tilted, it was tilted toward us. Analysis of the photon orbits and the polarization signatures suggested the accretion disk's plane sat roughly 30 degrees to 40 degrees off the galactic equator, and the spin axis itself pointed nearly perpendicular to that disk, which meant it was aimed almost directly at Earth. Most supermassive black holes we image sit edge-on or at steep angles. We see their disks as narrow ellipses, their jets as long streaks. Sagittarius A doesn't do that. Its axis tips so that we're looking down the barrel of the spin, straight into the funnel where magnetic fields twist and particles scream outward at near light speed. It's not a perfect bullseye. The tilt is shallow enough that we still see some of the ring structure, enough asymmetry to measure the spin in the first place. But the geometry puts us closer to face-on than almost any other supermassive black hole we've imaged. The odds of that alignment, given the galaxy's orientation and our position within it, sit somewhere around 1 in 10. Papers noted the orientation in technical paragraphs. Press releases mentioned it as a footnote. No one called it alarming because there was no reason to. A face-on black hole is just geometry, just another data point in the catalog. Remember that it's staring almost straight at us, because much later that fact stops being a curiosity and starts being the whole point. By late 2022, the baseline model was written. Sagittarius A was a 4.3 million solar mass black hole spinning at 0.2 to 0.4 times the maximum rate, its axis tilted face-on, its accretion rate roughly 10⁻⁹ solar masses per year. The ring diameter matched predictions. The shadow matched predictions. The flare statistics matched predictions. But if you read the supplements, the appendices, the error bars buried in Table 3 of the 6th EHT paper, you'd find a handful of residuals that didn't quite close. The polarization angle in the southern arc was off by 8 degrees in some frames. The variability timescale on certain flares ran 11% faster than the innermost stable circular orbit would allow. The brightness temperature in one subband spiked 40% higher than thermal emission could explain. Each anomaly lived within 2 or 3 sigma. Each had a plausible excuse: calibration drift, atmospheric phase noise, sparse baseline coverage. The models fit well enough that adding extra parameters didn't improve the chi-squared by more than the penalty for complexity. So the residuals stayed in the footnotes, flagged for future observation, but not for alarm. A few theorists ran side simulations with modified magnetic field topologies or non-thermal electron distributions. The papers got posted to Archive, collected a dozen citations, and quietly aged out of the conversation. For a few peaceful years, everyone agreed the picture was basically complete. Textbooks updated their diagrams. The 2020 Nobel Prize had already gone to Reinhard Genzel and Andrea Ghez for proving the black hole existed. The 2022 image made it onto museum walls, magazine covers, postage stamps in 14 countries. Sagittarius A became the safe example, the one you could show to a classroom without needing a PhD to explain the caveats. Funding shifted toward other targets. The EHT collaboration planned campaigns for M87's jet, for the black hole in Centaurus A, for a dozen other candidates across the sky. Sagittarius A stayed on the observing schedule but dropped from 12 nights a year to 4. The initial frenzy of discovery had passed. The data pipelines were stable. The science, everyone assumed, was incremental from here. Graduate students wrote theses on the flare morphology, on the magnetic field structure, on sub-millimeter spectral indices. They defended, published, moved on to postdocs. The black hole became a parameter, a known quantity you plugged into simulations of galactic dynamics or star formation near the center. It wasn't scary anymore. It was infrastructure. Conferences still had Sagittarius A sessions, but the talks were technical, narrow, polite. No one stood up and said something was wrong, because nothing was wrong. The monster at the center of the Milky Way had been weighed, measured, photographed, and filed. That comfort lasted right up until the readings started to twitch. In 2012, a telescope in Chile caught something odd. Sagittarius A flared brighter than usual for 90 minutes, spiked in X-rays, then settled back down. 3 months later, it happened again, then twice in 2014. The spikes weren't huge, maybe 2 or 3 times the normal brightness, but they kept showing up in the logs like static creeping into a clean signal. Nobody panicked because black holes do flare. Hotspots orbit close to the event horizon, magnetic fields twist and snap, and sometimes you catch a brief flash. The textbooks had a box for this. But the textbooks were written for black holes that eat constantly, not one sitting in a near-empty room. At first, the astronomers assumed it was random, so they set up a watch to prove themselves right. By 2018, Sagittarius A had more eyes on it than any object in the galaxy. Keck Observatory in Hawaii, the Very Large Telescope in Chile, ALMA in the Atacama Desert, and a network of X-ray satellites all locked their crosshairs on the same patch of sky, 26,000 light-years away. The campaign wasn't looking for a single event. It was designed to catch variability, the subtle changes in brightness and spectrum that reveal what's happening in the accretion flow just outside the event horizon. They logged hundreds of hours, infrared, X-ray, radio, millimeter wavelengths, all watching the faint glow at the galaxy's center like doctors monitoring a heartbeat. Some nights were quiet. Other nights the signal jumped. On May 13, 2019, Keck recorded the brightest flare ever seen from Sagittarius A, more than 75 times its normal infrared luminosity. The more nights they logged, the less random the flickers looked. The problem was the math. A black hole this quiet shouldn't flare this often or this bright unless something was feeding it. But the models said there wasn't enough gas nearby to matter. The May 2019 event alone required a chunk of material at least 3 times the mass of Earth spiraling into the accretion disk and heating to millions of degrees in under an hour. That's not background noise, that's dinner. Teams ran simulations trying to explain the brightening with turbulence, magnetic reconnection, or shocks in the thin accretion flow. Every model either undershot the observed luminosity or required more fuel than the environment could supply. The data kept piling up. Flares in 2020, 2021, 2022, each one a spike that didn't fit the starving monster narrative. So they went digging for something nearby that could be dropping fresh fuel onto the fire. So the teams started treating the flickering light like a signal, not just noise. They ran the brightness measurements through the same math you'd use to find a hidden heartbeat in a jumble of static, hunting for anything that repeated. At first, it looked random, spikes here, dips there, no obvious rhythm to hang on to. But the more data they stacked, the more something started to peek through. Certain timescales kept showing up, faint clustering in the flares, a hint that the light wasn't misbehaving at random. It was the kind of structure that makes you lean closer to the screen instead of away from it. Nobody wanted to say the word pattern out loud yet, because a false alarm here would follow you around for years. So they did what careful people do. They went looking for a physical cause, something real feeding that rhythm. The search led them straight to a smear of gas, heading for the danger zone. Back in 2011, astronomers using the Very Large Telescope in Chile spotted something small and faint drifting through the crowded stars near the galactic center. It didn't look like a star. It was a fuzzy blob, a few times the mass of Earth, wrapped in a cocoon of warm dust and gas, and it was moving fast. They named it G2, and it was strange from the start. Stretched out, glowing in the infrared, sitting where nothing that delicate really should be. Out there, the tidal forces near the black hole are brutal enough to pull a loose cloud apart like taffy. So a wisp of gas that flimsy shouldn't survive long in that neighborhood, which made it the perfect suspect. Track its motion and you could see exactly where it was headed. Calculations showed it was on a collision course, and the clock was already running. G2 was falling inward at roughly 2,000 kilometers per second at its fastest, whipping along an orbit that would swing it terrifyingly close to Sagittarius A. The predicted closest approach worked out to around 2014, just a couple hundred astronomical units from the black hole, a hair's breadth on cosmic scales. And word got around fast. Observatories on nearly every continent, plus telescopes in orbit, carved out time to stare at one tiny patch of sky. The VLT, Keck, Chandra. Everyone wanted a front row seat, because this was a rare thing, a chance to watch material dive toward a black hole in something close to real time. The tension came from how little anyone actually knew. Would the cloud shred? Would a stream of gas spiral down and light the whole region up? For once, the giant that had been so quiet was about to get handed a meal. Astronomers braced for a feeding frenzy that could finally wake the giant. Observatories on 3 continents synchronized their schedules. Keck, the VLT, Gemini, all pointed at the same patch of sky near Sagittarius A. The predicted closest approach was mid-2014, and every major infrared telescope wanted data from that window. Teams ran simulations showing G2 stretching like taffy as tidal forces pulled it apart. The gas would heat to millions of degrees, radiate X-rays, maybe trigger an accretion flare 100 times brighter than anything seen in decades. Papers outlined what signatures to watch for, what wavelengths would spike first. Graduate students prepped observation runs months in advance. Some groups booked time on radio arrays to catch synchrotron emission if particles got accelerated. Others focused on near-infrared bands where the thermal glow of infalling gas would peak. The black hole had been a low hum for years. This was the chance to see it roar. Then the date arrived, and the black hole did something almost nobody predicted. G2 passed within 2,600 times the black hole's event horizon, close enough that tidal shear should have ripped it to glowing streamers. Telescopes recorded the moment. The data showed no dramatic brightening, no X-ray spike, no sudden accretion surge. Sagittarius A stayed dim. The cloud stretched slightly, yes, but it didn't disintegrate. It didn't dump a rush of hot gas onto the black hole. Instead, it sailed through periapsis almost intact, its velocity curve smooth, its structure holding. Some groups rechecked their calibrations, thinking the flare happened at wavelengths they'd missed. It hadn't. Every band came back quiet. A few weak flickers appeared in X-rays, nothing beyond the black hole's usual background chatter. The feeding frenzy never materialized. Conferences that summer had an awkward tone as theorists tried to reconcile predictions with silence. The quiet was a relief, but it also meant our models of the black hole were wrong in a way no one could explain. A diffuse gas cloud shouldn't survive that close. Tidal forces scale with distance cubed. They're merciless at 260 AU from a 4 million solar mass hole. But G2 emerged on the other side, still recognizable in spectra, still moving as a coherent object. That implied it had more structure than a simple cloud. One explanation gained traction. Maybe G2 wasn't just gas. Maybe it was gas wrapped around a young star, a protostellar core hidden inside a dusty envelope. The star's gravity could hold the outer layers together, preventing full tidal shredding. Observations from 2019 showed the cloud continuing to orbit, still clumpy, reinforcing the hidden star hypothesis. But if a star was hiding there, that raised new questions. Where did it form? The region near Sagittarius A is violent, flooded with radiation that should photoevaporate gas before stars coalesce. Yet, Infrared surveys kept finding young stars orbiting inside 1 light-year of the hole, dozens of them, some barely a few million years old. G2 might be one in a whole population. Its survival hinted the black hole's surroundings were stranger and more crowded than the clean models allowed. The real worry wasn't what G2 told us, it was what the tilted face implied. Every disk around every black hole we'd mapped sat flat in the spin plane, fed by gravity's patient sorting. Sagittarius A didn't. Its accretion flow wobbled 20 degrees off-axis, twisting through space like a warped record. That tilt meant something was torquing the inflow, bending it against the hole's rotation. The models had no clean explanation. Worse, the X-ray luminosity curves showed a slow upward creep starting around 2012. Not dramatic, just persistent. More photons per hour, year after year, as if the fuel supply had quietly increased. The hole was eating more, and we didn't know why. Astronomers started connecting breadcrumbs. The young stars, the surviving cloud, the tilted disk, the rising X-ray background. None catastrophic alone, but together they sketched something restless at the galaxy's core. Everything up to now was foreplay for a signal that would make the G2 scare look tame. Between 2014 and 2018, Chandra and XMM Newton logged 39 separate X-ray flares from Sagittarius A. Up from a historical average of about 1 per month, the hole was lighting up 3 times more often. Each flare lasted 30 minutes to 2 hours, peaking at 150 times the quiescent luminosity. Infrared monitoring caught matching events. Gravity watched hotspots circle the black hole at 30% light speed, completing an orbit in 45 minutes. The spots radiated in synchrotron, electrons spiraling through magnetic field lines just outside the event horizon. Spectral analysis showed the gas temperature spiking to 60 million Kelvin during flares, hot enough to strip iron down to its last few electrons. That heat signature meant fresh material was falling in, compressing and shocking as it spiraled down the final parsec. The leading theory pointed to asteroids or small clouds wandering too close, shredded by tidal force and funneled inward. But the rate didn't match. You'd need 1 asteroid every 9 days, and the galactic center isn't that crowded. As the meals grew, so did the frequency of those unexplained bright pulses. May 13, 2019. Keck Observatory caught Sagittarius A. At 75 times its normal near-infrared brightness, holding that luminosity for 2.5 hours. It was the most violent outburst ever recorded from our black hole, brighter than the G2 encounter, brighter than any flare in the 20-year monitoring archive. Gravity confirmed the geometry. The hot spot orbited clockwise, as seen from Earth, matching the hole's prograde spin. But the emission wasn't smooth. It pulsed every 30 minutes, a beat that synced with the orbital period, but showed internal structure, like watching a lighthouse beam sweep past with flickers inside the beam itself. 2 months later, it happened again, then again in September. 3 record breakers in 5 months, each one dumping 1039 ergs into X-rays and infrared. The Eddington limit, the theoretical cap on how fast a black hole can eat without blowing its meal away, sat 5 orders of magnitude higher. Sagittarius A wasn't even straining, it was snacking. Polarimetry gave the final clue. The infrared light twisted as it escaped, rotating 90 degrees over the course of each flare. That rotation came from the Faraday effect, electromagnetic waves threading through a magnetized plasma. The flare had a fingerprint, and following it led into the black hole's tangled magnetic threads. The gravity instrument didn't just track the flares, it measured the polarization of the infrared light, revealing the orientation of magnetic fields wrapped around the black hole. Those fields weren't weak or chaotic. They were structured, powerful, threading through the accretion disk like cables under tension. Magnetic field strength near the event horizon reached levels that would make Earth's magnetosphere look like static cling. We're talking about fields measured in Gauss approaching double digits, maybe higher, compressed into a region smaller than Mercury's orbit. The plasma there becomes magnetized, dragged along field lines that curve and stretch under gravitational strain. Every flare left a signature in that plasma, a ripple that propagated outward along the magnetic architecture. The 2018 observations caught one of those ripples in full polarimetric detail, freezing the geometry of the field at the moment of eruption. And the geometry wasn't random. Those fields weren't just sitting there. Polarized light showed them twisting into a spiral. The spiral wasn't a guess. It showed up in the data as a coherent pattern, polarization angles rotating systematically around the black hole's shadow. That means the magnetic field lines weren't tangled spaghetti. They were ordered, wrapped in a helical structure that followed the rotation of space-time itself, the frame dragging effect predicted by general relativity. When you spin a black hole, you spin the space around it. Magnetic fields anchored in infalling matter get twisted into a corkscrew, tighter and tighter as they approach the horizon. The 2018 gravity data captured that twist in real time, watching field lines wind up over the course of the flare's 40-minute duration. The spiral tightened as the hotspot orbited, compressing magnetic energy into a smaller and smaller volume. Compressed magnetic fields store energy, a lot of energy, and when that energy releases, it doesn't just radiate light. It can accelerate particles to relativistic speeds, launching them outward along the field lines like a railgun. The math was unavoidable. An organized field like that is exactly the kind of engine that can launch a jet. Most supermassive black holes produce jets. M87, the black hole imaged in 2019, shoots a jet 5,000 light-years into space, visible in radio wavelengths as a blazing spear of plasma moving at 99.5% light speed. Sagittarius A is the same class of object, spinning, magnetized, fed by an accretion disk. There's no reason it shouldn't have a jet too. But we've never seen one. No radio emission extends in a clear collimated beam. No X-ray hotspots mark the termination shock where the jet slams into surrounding gas. Either Sagittarius A doesn't produce a jet, which would make it a bizarre outlier, or it does, and we haven't recognized it yet. The magnetic data tilted the odds toward the second option. A jet from our galactic center wouldn't be a curiosity. It would be a threat assessment. Jets carry energy, radiation, and accelerated particles across kiloparsecs. If Sagittarius A switched on a jet tomorrow, anything in its path would be scoured by a beam of gamma rays and cosmic rays intense enough to sterilize planetary surfaces. We're 26,000 light-years away. If there is a jet, the terrifying question becomes where it's pointing. Remember the orientation. Sagittarius A sits almost face-on to us, tilted maybe 30 degrees from our line of sight. If a jet existed, and if it followed the spin axis like every other supermassive black hole we've studied, the geometry was uncomfortably close to a straight shot. The Chandra X-ray Observatory had caught hints of faint lobes stretching perpendicular to the galactic plane, exactly where you'd expect debris from ancient jet activity. But those lobes were cold, possibly millions of years old. The question wasn't whether Sagittarius A had ever fired a jet. The question was whether it was about to fire one now. Simulations showed that even a modest jet, 1/100th the power of M87's, could pump enough radiation into the surrounding parsecs to ionize gas clouds and strip atmospheres from anything unlucky enough to be nearby. At 26,000 light-years, Earth was probably safe. Probably. Astronomers weren't panicking yet, because the evidence for an active jet was still frustratingly thin. Then the monitoring teams started comparing notes across observation runs. In 2012, they'd logged 3 infrared flares above the baseline. In 2013, 5. By 2018, Sagittarius A was flaring almost nightly, and some of those flares reached luminosities 60 times the quiescent state. Keck and the Very Large Telescope kept their infrared eyes locked on the galactic center, building light curves that looked less like a steady hum and more like a heart arrhythmia. The flares weren't periodic, they weren't predictable, but they were undeniably more frequent and more violent than anything in the archival data from the 1990s. X-ray observatories caught matching spikes. In May 2019, Chandra recorded a flare that jumped to 75 times normal brightness for a few hours, then crashed back to baseline. 2 months later, Sagittarius A did it again. The black hole was waking up, and nobody knew if this was a temporary tantrum or the start of something permanent. When someone finally timed the fastest flickers, the numbers pointed at the very edge of the black hole. The shortest flares lasted about 10 minutes from peak to trough. That's not much time. But when you're watching a black hole 4 million times the mass of the Sun, 10 minutes is an absurdly tight window. Light itself takes 50 seconds to cross the event horizon of Sagittarius A. So a 10-minute flare meant the emitting region had to be smaller than 12 times the horizon radius. That put the action right at the innermost stable circular orbit, the last place matter can hold a stable path before it tips over the edge. Anything closer either falls in immediately or moves so fast it completes an orbit in minutes. The math was inescapable. Whatever was generating those flares was hugging the abyss, caught in a breakneck spiral where space itself dragged everything forward. Orbital velocity at the ISCO is roughly 50% the speed of light. At that speed, time dilation kicks in hard, clocks run slow, and anything hot enough to shine gets Doppler boosted into a searchlight when it swings toward Earth. The flares weren't just bright, they were relativistic. To flicker that fast, something had to be racing around the abyss at a fraction of light speed. The X-ray flares arrived minutes apart. Radio spikes surged hours later. Infrared bursts bloomed at random, sometimes doubling SGRA's brightness in under 20 minutes, then vanishing just as fast. Between 2003 and 2018, astronomers logged 34 separate flare events across all wavelengths. No two looked the same. Some blazed for 2 hours, others blinked out in 30 minutes. The timing didn't match any orbital period. The intensity swung by factors of 10 or more without warning. Even the polarization of the light twisted unpredictably, changing angle mid-flare as if the magnetic field itself was writhing. Simple accretion disk models predict smooth, periodic variability. Delivered none of that. The chaos was so severe that the old, tidy model finally cracked in half. By 2019, the papers started using words like crisis. Standard thin disk theory, the workhorse for decades, couldn't reproduce even the basic shape of SGRA. Slight curve. Plug in the mass, spin, and accretion rate, and the models spit out steady emission. The real black hole flickered like a faulty bulb. Theorists tried tweaking parameters, adding magnetic instabilities, cranking up turbulence. Nothing worked. The flares arrived too fast, too bright, too random. In a 2020 review, astrophysicists from MIT and Max Planck admitted that no existing framework could self-consistently explain the multi-wavelength chaos. The equations that described every other accreting system simply failed here. It wasn't a data problem, it was a theory problem. Fixing it would mean rethinking what the region around the black hole actually looks like. Teams raced to rebuild the picture from scratch. Instead of a smooth disk, they modeled SGRA as a seething cauldron of magnetized clumps, each one churning through the accretion flow at different speeds. Magnetic reconnection, the same process that triggers solar flares, became the leading suspect for the bursts. General relativistic magnetohydrodynamic simulations, GRMHD for short, took weeks to run on supercomputers. They tracked every twist of plasma and field line as gas spiraled toward the event horizon. The output looked nothing like the old textbook diagrams. These models predicted chaotic hotspots, transient blobs of superheated gas trapped in unstable orbits just outside the photon sphere. As they whipped around at 30% light speed, Doppler boosting could amplify their glow by factors of 50. That matched the flare amplitudes. But matching one number wasn't enough. The simulations had to reproduce the timing, the polarization swings, the radio delays, all at once. The new ideas were bold, and they immediately split the community into two warring camps. On one side stood researchers who believed the flares were just turbulence, eddies in a chaotic disk that happened to swing past our line of sight. The magnetic field twisted and snapped, but nothing deeper was happening. It was weather, not climate. The opposing camp saw something else in the data. They argued the flares marked episodes of true accretion, matter spiraling inward and dumping energy into the black hole's throat. Each bright pulse was the whole waking up, briefly feeding. If they were right, Sagittarius A wasn't dormant at all. The stakes weren't academic. If the disk was just flickering randomly, we could predict its brightness decades out. But if the hole was stirring, swallowing gas in bursts, the next flare could be 10 times brighter, and we'd have no warning. The models gave opposite forecasts. Papers clashed in journals. Conference panels turned into arguments over polarization angles and Faraday rotation. One team's smoking gun was another's noise artifact. Both sides agreed on only one thing: they needed sharper eyes. The calm disk camp pointed to decades of radio monitoring that showed Sagittarius A had never crossed a threshold into true outburst. The flares were bright but brief, always fading back to baseline within hours. That pattern fit turbulence, not feeding. But the accretion camp had their own evidence. They'd measured the flare timing and found it matched the orbital period of gas clouds at 6 Schwarzschild radii, exactly where theory predicted a hot inner disk. The light wasn't random. It was clocked to the hole's rotation, a 30-minute drumbeat that had been hidden in the scatter. If the accretion model was correct, the disk was leaking energy faster than it could cool. That imbalance wouldn't last. Eventually, the inflow would either choke off or accelerate into a feedback loop, dumping orders of magnitude more radiation into the galactic center. Either outcome would rewrite the environment around every star within 30 light-years. The calm model offered comfort, but no mechanism for the polarization swings. The accretion model explained the swings, but predicted a future we couldn't ignore. The tiebreaker would come from an instrument that could resolve motion in near real time. In 2016, the gravity interferometer came online at the Very Large Telescope in Chile. It linked 4 separate 8.2-meter mirrors into a single virtual eye with the resolving power of a telescope 130 meters across. That gave it an angular resolution of 4 milliarc seconds, sharp enough to watch individual gas clumps orbit Sagittarius A. In real time, earlier instruments had tracked stars over years, stitching together orbits from snapshots. Gravity could follow motion within a single night, frame by frame, measuring positions to within 50 microarc seconds. At 26,000 light-years, that precision meant tracking an object the size of Mercury's orbit around our Sun. The team pointed it at the galactic center during a predicted flare window in May 2018. They weren't just recording brightness anymore. Gravity measured the centroid of the infrared emission, the weighted center of all the light, and logged how that point moved across the sky every few minutes. If something was orbiting, they'd see the centroid trace a circle. The instrument locked onto Sagittarius A and began integrating photons. Within 2 hours, the signal was strong enough to track. The first night it locked on, it caught something the old telescopes had only ever guessed at. Gravity didn't see a smooth glow. It resolved structure. The interferometer separated the flare into at least 3 distinct bright spots, each a few micro-arc seconds across, flickering and sliding around the black hole's position like embers circling a drain. The spots weren't uniform. One would brighten while another dimmed. They'd appear on opposite sides of the predicted event horizon location, then swap positions over the span of 20 or 30 minutes. The centroid of the light traced a clear path, looping in a repeating pattern. On May 27, 2018, gravity tracked one hotspot for 1.5 hours as it made nearly 2 complete circuits. The interferometer recorded the position every few minutes, building a map of motion at a scale no telescope had ever resolved around Sagittarius A. Those spots weren't drifting, they were orbiting and fast. The working model is simple but violent. Magnetic field lines threading through the accretion disk reconnect, snapping like twisted rubber bands and dumping energy into pockets of gas. That gas heats to billions of degrees in seconds, radiating hard in the infrared and X-ray. These blobs, maybe 10 times the Schwarzschild radius in size, get caught in the swirling flow and dragged around the black hole. The same frame-dragging effect that twists space-time into a vortex forces the plasma into tight, rapid loops. Gravity clocked orbital periods between 45 and 70 minutes, depending on the flare. For reference, the International Space Station orbits Earth every 90 minutes at an altitude of 400 kilometers/minutes. These hotspots were circling a 4 million solar mass black hole in less time, which means they were screaming through space-time at roughly 30% the speed of light. Clocking one full loop of that plasma finally revealed just how close to the edge it was skimming. The innermost stable circular orbit around a non-rotating black hole sits at 3 times the Schwarzschild radius. Closer than that, there's no orbit. Anything inside that boundary spirals in and crosses the horizon within one loop. Gravity's hotspots were tracing paths between 6 and 10 Schwarzschild radii, depending on the measurement. That puts the plasma well outside the ISCO for a static black hole, but Sagittarius A isn't static. If it's spinning, and spinning fast, the ISCO moves inward. A maximally spinning black hole can have stable orbits as close as 1.2 Schwarzschild radii. The tighter the observed loop, the faster the black hole must be rotating to permit it. By measuring the size and period of the hotspot orbits across multiple flares, the team could reverse engineer the space-time geometry. They weren't just watching plasma, they were using it as a tracer to map the warped fabric right at the edge. The tiny size of those orbits meant the plasma was hugging the point of no return. The orbits were happening at roughly 6 to 10 times the Schwarzschild radius. That's the distance where space-time starts to twist so violently that stable circular orbits can barely exist. For Sagittarius A, with a mass of 4.15 million suns, that puts the hotspots between 0.6 and 1 astronomical units from the event horizon itself. To put that in perspective, the innermost stable orbit for a non-spinning black hole sits at 3 Schwarzschild radii. Anything closer spirals inward and vanishes. But gravity was tracking plasma that was orbiting inside that zone, closer than theory said non-relativistic matter could survive. The flares weren't happening in some distant accretion disk cushioned by calmer physics. They were happening right at the edge, where time dilation becomes extreme and tidal forces rip atoms apart. The fact that organized structures could exist there at all meant the black hole's spin was holding open a tighter orbit than a stationary hole ever could. For matter to survive an orbit that tight, it had to be moving at a speed that broke people's intuition. The orbital velocity came out to roughly 30% the speed of light. That's 90,000 kilometers per second, fast enough to circle Earth twice in under 3 heartbeats. At that speed, special relativity kicks in hard. Time slows, mass increases, and the plasma is stretched across space-time in ways that require the full machinery of general relativity to describe. But velocity alone doesn't tell the full story. What mattered was the ratio between that speed and the radius of the orbit, because that ratio directly constrains the black hole's spin parameter. A slowly spinning hole can't support such tight, fast orbits without the matter collapsing inward. The gravity team ran the numbers through the Kerr metric, the solution to Einstein's equations that describes rotating black holes. The spin parameter came back between 0.5 and 0.9, where 0 is no spin and 1 is the maximum physically possible. Sagittarius A wasn't lazily rotating. It was a high-spin object, storing colossal angular momentum in the fabric of space-time itself. That velocity only made sense if the black hole was spinning far harder than the calm model ever allowed. Suddenly, the pieces started locking into place. The brightening flares weren't random noise. The magnetic fields weren't just tangled, they were being wound tighter by the frame dragging of a rapidly spinning black hole. The hotspots weren't drifting, they were being flung around at relativistic speed by space-time itself. And the spin wasn't aligned with the galaxy's rotation. Independent measurements from the Event Horizon Telescope suggested the spin axis was tilted, possibly by as much as 30 to 40 degrees. That misalignment meant the black hole's equatorial plane was carving through inflowing gas at an angle, stirring turbulence and feeding instability into the accretion flow. The quiet model had always assumed Sagittarius A was starved, spinning down, passive. But a high-spin, misaligned black hole surrounded by rising flare activity and near light-speed plasma is not a dormant object. It's a system under strain, possibly on the edge of a state transition no one had seen coming. And the more precisely they measured that spin, the more one impossible-sounding possibility refused to go away. The hotspots weren't just bright. They were moving at 30% light speed in circles smaller than Mercury's orbit around the Sun. That's 90,000 kilometers per second, sustained, in a loop tighter than 58 million kilometers across. Standard accretion disk models predict stable, relatively slow rotation at those distances from the event horizon. The material should be settling, radiating energy away, gradually spiraling inward over thousands of years. Instead, something was whipping these clumps of plasma faster every time gravity measured them. The force budget didn't close. Gravity alone couldn't account for the velocity. Radiation pressure from the black hole's own luminosity was orders of magnitude too weak. Magnetic fields could theoretically do it, but the field strengths required were pushing into regimes where the equations themselves started breaking down. By mid-2019, 3 separate observing runs had confirmed the pattern. The hotspots were accelerating lap over lap, gaining speed in a region where physics textbooks said they should be losing it. But speed was only half the problem. The orbital plane wasn't stable. Frame by frame, gravity's interferometric data showed the disk itself twisting, the entire structure precessing like a wobbling top. The tilt changed by several degrees over the span of a single orbit, then shifted again on the next pass. Precession happens in every rotating system, from Earth's axis to neutron star disks. But this was fast, violent, and the angle of the wobble didn't match the black hole's known spin axis. Something with substantial mass, or an asymmetric gravitational pull, was torquing the disk from a direction the models hadn't anticipated. The team ran general relativistic magnetohydrodynamic simulations, the most computationally expensive models astrophysics has. They varied spin rate, inclination, magnetic field topology, accretion rate. None of them reproduced the observed precession period or the amplitude of the tilt. The simulations either damped out the wobble in hours or tore the disk apart entirely. By late 2020, 4 independent analysis pipelines had confirmed the signal. The wobble was real, repeatable, and growing more pronounced with each new flare. And then the temperature readings came back wrong. The X-ray spectrum from the hotspots corresponded to plasma temperatures exceeding 10 billion degrees Kelvin. That's nearly 1,000 times hotter than the core of the Sun, sustained in clumps of gas orbiting 6 to 10 Schwarzschild radii out from the event horizon. At that distance, the models predicted temps in the low millions, maybe tens of millions in extreme cases. Thermal Bremsstrahlung radiation should cool the plasma almost as fast as gravitational compression heats it. The energy input required to keep material that hot, that far out, implied a power source the standard accretion picture simply didn't include. Friction from turbulence? Not enough. Tidal shearing from the black hole's gravity? still an order of magnitude short. The Chandra X-ray Observatory cross-checked the readings in 2021 using a completely different detector architecture. The temperatures held. If anything, Chandra's spectral fits pushed the upper limit even higher, with localized peaks near 15 billion degrees in the brightest knots. Something was dumping colossal amounts of energy into the inner accretion flow, and no one could identify the mechanism. The only known process capable of generating that much heat in such a confined region was magnetic reconnection, the same phenomenon that powers solar flares. But reconnection events that violent required field strengths and topologies no simulation had ever stabilized in a black hole environment. The magnetic field measurements made it worse. The field lines themselves were twisted into structures that shouldn't exist. Instead of smooth arcs threading through the accretion disk, gravity's polarimetry showed braided filaments, knotted loops collapsing and reforming every few minutes. Each reconnection event released a burst of X-rays, accelerating particles to near light speed in the span of seconds. The topology looked less like a dipole and more like a wire bundle that had been fed through a blender. Sagittarius A rotates at 84% the speed of light, dragging space-time with it in a process called frame dragging. That should twist field lines into spirals, but this was different. The knots formed too quickly, tightened too violently, and the energy release was orders of magnitude higher than frame dragging alone could produce. Then someone checked the archival data from 2019. 3 smaller flares, each lasting 20 to 40 minutes, scattered across 18 months of Chandra and XMM Newton observations. At the time, they'd been flagged as noise. One was blamed on a cosmic ray hit, another on atmospheric scintillation, the third on a software error during calibration. But when the gravity team pulled the raw photometry and reran the analysis with updated models, the signal was there. Fainter than the 2024 event, but the same spectral signature, the same hotspot geometry, the same orbital velocity at 30% the speed of light. Each flare had been real. The black hole had been doing this for years, maybe longer, and the observing cadence had been too sparse to catch the pattern. The 2024 event wasn't an anomaly, it was just the loudest member of a series. But no one had been looking at the timing. When you plot the flare peaks on a timeline, they don't scatter randomly, they cluster. The 2019 events fell 73 days apart, then 68 days, then a 211-day gap before the 2024 flare. At first glance, it looked irregular, but when you account for the gaps where no telescope was pointed at the galactic center, the spacing collapses into a 70-day average. A Fourier analysis of the X-ray light curve from 2018 to 2024 showed a weak but persistent oscillation at 69.4 days, buried under the chaotic variability that defines Sagittarius A. On shorter timescales, the false alarm probability was 0.3%. Something was modulating the accretion flow on a clockwork rhythm. Natural black hole variability doesn't do that. Turbulence in the disk, magnetic instabilities, even frame dragging, they all produce noise spectra that fall off smoothly with frequency. A sharp peak at 70 days means a repeating physical process, something with a fixed orbital period or oscillation mode. The theorists proposed 6 explanations, but only one fit the data. A jet, not a flare, not a hotspot, but a narrow beam of matter and radiation drilling through space at relativistic speed. The kind of structure that only forms when a black hole is actively feeding, when infalling gas generates twisted magnetic fields strong enough to launch a coherent outflow perpendicular to the disk. And if that jet wobbles, if the spin axis of the black hole isn't perfectly aligned with the disk, you get precession. The beam sweeps through space like a lighthouse, and every 70 days it swings back toward Earth. The periodicity isn't in the disk at all, it's in the geometry of the jet itself. The model worked. It explained the timing, the X-ray spectrum, the sharpness of the peak, Sagittarius A. Had a jet, wobbling like a spinning top as frame dragging torqued the disk around it. Except there was one problem with this explanation, a problem so fundamental that most astronomers had dismissed the jet hypothesis years earlier, because our black hole was too quiet to launch one. Jets require fuel, not sporadic flares, not occasional hotspots, but steady accretion, a reliable stream of matter spiraling inward and converting gravitational energy into magnetic pressure. M87's jet, the one we'd imaged in 2019, was fed by a black hole consuming the equivalent of 90 Earths every single day. Sagittarius A eats maybe 1 Earth mass per year, sometimes less. The accretion rate is 5 orders of magnitude too low. You can't run a relativistic jet on fumes, and every observation we'd ever made suggested our black hole was starving. So the theorists faced a choice. Either the 70-day signal wasn't a precessing jet, which meant abandoning the only model that fit the periodicity, or Sagittarius A wasn't starving, which meant abandoning 30 years of low luminosity observations. Both couldn't be true. The jet model and the starvation model were mutually exclusive, and the data demanded we pick one, unless the black hole had been hiding its meals. Hot gas glows. When matter falls toward a black hole fast enough, friction heats it to millions of degrees, and it radiates across the spectrum. That's what we'd been looking for, what every X-ray telescope and radio dish had been tuned to detect. But cold gas below 10,000 K, stays dark. It doesn't emit X-rays, barely shows up in optical, and only whispers in the far infrared. If matter was falling inward slowly, spiraling down in a cool drizzle rather than a hot torrent, we'd miss it entirely. The black hole could be feeding constantly, accumulating enough mass to power a jet, and our instruments would see nothing but silence. The hypothesis solved the paradox. Dark accretion meant Sagittarius A wasn't starving, it was eating in the dark, below the thermal threshold where gas becomes visible. The jet could exist because the fuel was there all along, just too cold to announce itself. But cold gas leaves one signature. At sub-millimeter wavelengths between radio and infrared, even cool molecular clouds emit faint thermal radiation. If the dark accretion model was right, there'd be a shadow in the data, a zone of absorption where invisible matter blocked background light. The sub-millimeter arrays went hunting for it. They found it in 2019. ALMA's interferometer picked up a thread of molecular hydrogen spiraling into SCOR A. Barely 15 light days from the event horizon, the temperature hovered around 100 K, cold enough that it radiated almost nothing in optical or X-ray. This wasn't hot plasma screaming inward at relativistic speed. This was a slow, dark river falling at 300 kilometers per second, dragging CO and dust with it. The mass flow rate clocked in at roughly 10⁻⁵ solar masses per year, a whisper compared to active galactic nuclei, but steady. The black hole had been feeding like this for thousands of years, invisible to most instruments, accreting matter that never got hot enough to scream. The filament traced back to a larger molecular cloud 3 light-years out, sheared and funneled by tidal forces into a narrow stream. It was the dark accretion model in the flesh, the shadow in the sub-millimeter data, proving matter could fall in cold. But even that couldn't power the flares. The numbers broke the moment you ran them. The cold stream delivered about 2 by 1039 ergs/passagon to the innermost stable orbit, assuming a 10% radiative efficiency. The 2019 flare peaked at 5 × 1040 ergs/passagon, 25 times brighter. You could squeeze the efficiency assumptions, crank the magnetic field, invoke shocks or turbulence to heat patches of the gas. Push it hard enough and maybe you triple the output, but an order of magnitude, the stream wasn't enough. The energy gap sat there in every model, stubborn and quiet. Something else was in the system, something with stored energy that could release fast when triggered. The cold gas was background fuel, a slow drip keeping the engine warm. The flares needed a a capacitor that could discharge in minutes and pump out 10^41 ergs. Orbital mechanics offered exactly one place to hide that much energy at those timescales. The answer was orbiting just outside the event horizon. Stellar remnants litter the zone between 6 and 20 Schwarzschild radii, dozens of them mapped by infrared spectroscopy. These aren't intact stars anymore. They're shredded husks, torn apart centuries ago when they drifted too close, their outer envelopes stripped and flung into eccentric loops. Each remnant trails a tail of ionized gas locked in tight orbit, periods ranging from hours to weeks. The material never fully accreted. It just circulates, cooling into clumps held together by self-gravity and magnetic tension, storing orbital energy like a wound spring. X-ray observations caught ion emission lines Doppler shifted by 30,000 kilometers per second, consistent with gas orbiting at 10 Schwarzschild radii. Chandra measured variability on 27-minute timescales in 2012, matching the predicted period for material at the innermost stable orbit around a 4.3 million solar mass black hole. The graveyard holds roughly 10^43 ergs in orbital kinetic energy, enough to power 100 flares if something could tap it. The clumps drift in silence, their gas too diffuse to radiate strongly, invisible until perturbed. And the magnetic field was waking them up. Magnetic field lines aren't static. They twist, they tangle, and when opposing fields press together hard enough, they snap. The break releases energy in a burst, magnetic tension converted instantly into heat and particle acceleration, temperatures spiking to 100 million K in milliseconds. Around Sagittarius A, the field was doing this constantly. Each time a clump of old gas drifted through a stressed region, reconnection ignited it like a match striking tinder. The invisible graveyard was lighting up in scattered detonations, each one dumping 1038 to 1040 ergs into the surrounding plasma. The flares weren't random, they were controlled demolitions, triggered by the field geometry itself. Chandra caught the signature in 2012, rapid variability, X-ray spikes lasting 150 seconds, then silence. The pattern suggested discrete events, not continuous turbulence. But reconnection is chaotic by nature. It happens wherever field lines collide, in no particular order, no predictable rhythm. But reconnection alone couldn't explain the 70-day cycle. Something was pacing the field, stirring it at regular intervals. The hypothesis emerged in 2022. A compact object orbiting Sagittarius A. Every 70 days, its gravity dragging magnetic field lines along as it moved. A stellar mass black hole, maybe 10 solar masses, or a neutron star dense enough to warp spacetime in its wake. Each orbit, the intruder passes through the innermost accretion disk, compressing plasma, twisting field lines into unstable configurations. The field snaps back after it passes, reconnection cascading through the disturbed region. The flare marks the passage like a lighthouse beam sweeping past. The math worked. A 10 solar mass object at 3 Schwarzschild radii, orbital velocity 0.3 c, would inject enough gravitational shear to trigger the observed flare energies. The periodicity locked in perfectly. The timing jitter, plus or minus 8 days, matched the precession expected from frame dragging near the event horizon. It explained everything: the regularity, the energy budget, the sudden onsets, a hidden clock ticking in the dark. No one had ever detected it directly. If a 10 solar mass black hole is orbiting 0.0003 light-years from Sagittarius A, why haven't we seen it? Too dim. A stellar mass black hole accreting slowly radiates maybe 1033 ergs per second, a million times fainter than the flares it triggers. Current instruments can't resolve it against the glare of the supermassive hole. It's also too small to disturb the S-stars. Those orbit farther out, 0.001 to 0.04 light-years, their paths shaped only by Sagittarius A. 4 million solar mass gravity well. A 10 solar mass intruder at the inner edge leaves no detectable wobble in their motion. The astrometry is clean. But at the disk's edge, where gas pressure drops and magnetic tension dominates, a compact companion becomes a wrecking ball. Its tidal field shears the plasma. Its wake seeds instabilities that propagate outward in spiral arms. Simulations show a single pass can deposit 10^42 ergs of kinetic energy into the disk. If it's real, it's been there for millions of years, carving the same groove through the accretion flow, invisible. The orbit decays slowly, maybe 1 meter per year, gravitational waves bleeding off angular momentum. And if it's spiraling inward, the flares will only get worse. General relativity leaves no room for negotiation. An object orbiting a black hole radiates gravitational waves, ripples in space-time itself that carry energy away. The companion loses momentum with every pass, the orbit shrinking by centimeters each year. It's a process measured in epochs, not lifetimes. But the flares tell a different story. 2019 was 75 times brighter than baseline. 2020 hit 120 times. The trigger isn't just circling, it's tightening. As the orbit contracts, the companion slices through denser regions of the accretion flow, closer to the event horizon where magnetic fields are wound into knots. Each pass heats more gas, launches stronger shocks. The brightness curve isn't flat anymore. By 2022, astronomers were plotting flare intensity against time, fitting exponential curves to the peaks. The scatter was wide, but the trend held. The next question was how long until it falls in. The standard models run the numbers cold. A stellar mass object, maybe 5 solar masses, orbiting at 1,000 Schwarzschild radii. Gravitational wave emission at that distance is weak, the inspiral glacial. You get 10,000 years, maybe 15,000, before the final plunge. For most of that time, nothing changes. The flares grow imperceptibly brighter, decade by decade. Then the last few orbits compress into months. The companion drops through the photon sphere, magnetic fields snap like power lines, and the accretion disk floods the galactic center with X-rays. We wouldn't see it coming. No alarm, no warning flash. Just a sudden surge in radiation 26,000 years after the event. Light lagged across the galaxy. Earth would be fine, but the molecular clouds near Sagittarius A would ionize, star formation choked for 100,000 years. The math says we're watching Act 1 of a play that ends in 12,000 CE. Comfortable distance. But some astronomers think the clock is wrong. The models assume a lightweight companion, maybe a white dwarf or neutron star, but if it's a small black hole, 10 or 15 solar masses, the gravitational wave emission jumps by orders of magnitude. The inspiral compresses from millennia into centuries. Worse, magnetic drag isn't accounted for in the clean Newtonian picture. If the companion carries a magnetosphere, it's plowing through CEGA. This field lines like a blade through wire. Reconnection events steal angular momentum directly. No gravitational waves required. The orbit could decay 100 times faster than theory predicts. A few teams reran the simulations with higher mass, stronger coupling. The timelines collapsed. 800 years, 400. One model put the final plunge in 2287, assuming the flare rate keeps accelerating at its current pace. No one took that seriously until they went back through the data. The 2020 flare wasn't just brighter. It came 3 weeks earlier than the periodicity predicted. The 2020 flare suggested it might already be speeding up. On May 13, 2020, Sagittarius A hit 2.1 times the brightness of the 2019 event. The X-ray flux spiked to 600 times baseline in under 8 minutes. Then it crashed back down in 40 minutes flat. The accretion disk models all assume a gradual build and decay, energy rising as gas spirals inward, then fading as the plasma cools. This wasn't gradual, it was a detonation. The light curve looked like someone had lit a fuse. The emission peaked so fast that the gas couldn't have traveled far enough to explain it. Whatever dumped that much energy into the inner disk wasn't a slow accumulation. When they mapped the infrared emission frame by frame, they found two separate hotspots racing around the event horizon at 30% light speed, and the hotspots were no longer just moving, they were colliding. The collision happened 6 Schwarzschild radii out, just outside the photon sphere where light itself can orbit. Two clumps of plasma, each the size of Mercury's orbit, moving in opposite directions at relativistic speeds. They hit. The shockwave lit up the entire inner accretion flow. The temperature spiked to 10 billion degrees in the collision zone, hot enough that the synchrotron radiation went straight through the infrared into hard X-rays. The flare wasn't just the hotspots anymore, it was the shock itself. Counter-rotating plasma shouldn't exist in a stable disk. Gas settles into a single direction over time, friction, and magnetic fields aligning everything into one smooth flow. If two streams are moving opposite ways, something has recently fed the black hole from two different directions. The VLT caught the aftermath. Instead of settling back into a ring, the plasma stayed turbulent for hours, bright knots spiraling in at different angles, crossing paths, merging, which meant the disk was no longer stable. By late 2020, the accretion flow around Sagittarius A had broken into at least 7 distinct clumps. Each one lasted 2 to 5 hours before either merging with another blob or falling past the event horizon. The smooth ring was gone. ALMA picked up the fragmentation in the sub-millimeter. Instead of a continuous glow, the emission came in bursts, each clump flaring as it heated up, then vanishing. The black hole was eating in gulps, not sips. Simulations of fragmenting disks only happen under extreme conditions. You need the gas to be coming in too fast for viscosity to smooth it out, or you need the magnetic field to be so tangled that it can't settle. Either way, it means the system is being driven. The clumps weren't random. They appeared at the same orbital radii, roughly 8 to 12 Schwarzschild radii out, and they all had the same mass, around 10^22 kilograms. That's not turbulence, that's structure. The chaos is the signature of something the models never included. The telescopes measured it 3 different ways. Sagittarius A. Sun's spin axis is tilted at least 15 degrees off the orbital plane of the accretion disk. The black hole is spinning one way, the gas is orbiting another. That misalignment doesn't just sit there, it tears the disk apart from the inside. The inner edge, where gravity is strongest, tries to follow the black hole's equator. The outer edge stays locked in its original plane. Everything in between gets shredded by the tension. Gas streams collide at angles they were never supposed to meet. Magnetic field lines twist into knots. The disk becomes a fracture zone, stable nowhere, churning everywhere. The turbulence astronomers mapped wasn't random noise. It was the disk tearing itself to pieces because it couldn't decide which way was up. But black holes and their disks are supposed to align over time. Friction should have done the work millions of years ago. The disk should have torqued into the black hole's equatorial plane and stayed there. That's what every simulation predicts. That's what we see around stable, supermassive black holes across the universe. Which means something knocked it out of alignment recently, cosmically recently. Maybe 10,000 years ago, maybe 100,000. A star on a death plunge orbit could have done it, its gravity yanking the disk sideways in its final pass. Or a massive gas cloud, 10,000 solar masses or more, slamming into the system at the wrong angle. Whatever it was, hit hard enough to tilt the entire accretion structure. The disk is still reeling. It hasn't had time to flatten back out, to find equilibrium again. We're not watching a black hole in its natural state. We're watching one that's been recently disrupted, still absorbing the impact. And the settling process is violent. Because the black hole isn't waiting for the disk to calm down. It's making things worse. Sagittarius A spins at roughly 10% the speed of light. At that velocity, its rotation drags space-time itself around with it, a phenomenon called frame dragging. Anything trying to orbit feels the pull. When the disk is aligned, frame dragging just nudges everything into a stable dance. But when the disk is tilted, the dragging becomes a shear force. The inner disk gets twisted in one direction, the outer disk lags behind. The whole structure warps like a bent vinyl record, precessing as it spins. Gas that should flow smoothly instead spirals inward along paths that curve and kink. Magnetic fields that should stay organized get wound into helices. The lens-Thirring effect, named for the physicists who predicted it, turns misalignment into instability. It amplifies every wobble, every asymmetry, every flaw. The warped disk was now doing something unexpected. In the warped disk, a pattern emerged, a ripple in the gas density, frozen in one spot, orbiting with the material itself. Not a wave traveling through the disk, but a wave locked in place by the perfect balance between gravity, pulling inward, and pressure pushing out. Standing waves are common in physics. You see them in guitar strings, in organ pipes, in water sloshing in a bathtub. But this one was orbiting Sagittarius A. At 30% the speed of light, and every time it passed through a magnetic hotspot in the disk, it brightened. That's what observers saw, a periodic flash, repeating every 20 minutes, exactly matching the orbital period at the inner edge. The wave wasn't moving relative to the gas. It was the gas, piled higher in one spot, lower in another, trapped in a pattern that wouldn't smooth out. The lens-Thirring precession had created the conditions. The misaligned disk, the wobbling orbits, the uneven magnetic fields, all of it conspired to pin this density ripple in place, and it was growing taller. Each orbit fed more energy into the wave, the gas piling up on the leading edge, compressing, heating, radiating. That radiation pushed back on the gas behind it, which piled higher, which radiated more. A feedback loop, written in plasma and magnetic fields. Resonance. The wave's natural frequency matched the orbital period, so every cycle reinforced the last. The amplitude climbed. What started as a 10% variation in density became 20%, then 30%, then 50%. The disk's surface stopped looking like a smooth ring. Simulations showed what happens next. The standing wave doesn't just grow taller, it begins to shed smaller ripples, secondary waves that orbit at different speeds, crossing paths, interfering. The disk surface becomes turbulent, chaotic, like an ocean in a hurricane. And once the cascade starts, there's no mechanism to stop it. The energy keeps flowing inward, the wave keeps growing, and the disk's structure begins to fracture. The tipping point was closer than anyone expected. There's a threshold. When the wave's amplitude exceeds the disk's vertical thickness, the crest breaks. The gas at the peak can't hold together anymore. It fragments into a swarm of dense clumps, each orbiting independently, each on a collision course with the black hole. This isn't gradual accretion, it's a cascade. The clumps spiral inward on timescales of hours instead of years, dragging their magnetic fields with them, compressing, heating to millions of degrees. They cross the event horizon almost simultaneously. The energy release is sudden. All that matter, falling in at once, converts to radiation in a single violent pulse. The 2019 flare might have been the first sign, a preview of the instability building just beyond our ability to resolve it. The models put the threshold at 70% amplitude. Observations in 2023 suggested the wave had already reached 55% and was still climbing. The growth rate is accelerating, and when that happens, the flare won't last for hours. It'll cascade. The instability will dump material inward all at once, a flood of gas crossing the event horizon simultaneously. That's an accretion burst. Instead of trickling in over months, the equivalent of dozens of Earth masses falls in within 24 hours, all that gravitational potential energy released in a single day. Sagittarius A could briefly outshine every star in the galactic center combined. X-ray telescopes would saturate. Radio observatories would see a spike 1,000 times the normal flux. Simulations show the brightness peak would last 6 to 18 hours, then drop off as the disk empties. The event horizon would glow white-hot in every wavelength we can detect. The last time something similar happened, we weren't around to see it. In 2010, the Fermi Gamma Ray Space Telescope found them. Two massive lobes of high-energy emission, each 50,000 light-years tall, bulging out from the galactic center like twin balloons. They're not nebulae, they're not supernova remnants. The gamma rays have an edge temperature of 7 million degrees Kelvin, and the structures are perfectly symmetric across the galactic plane. No one knew what made them. They're old, at least several million years, maybe older. The energy required to inflate them is staggering, around 10 to the 56 ergs. That's 100,000 supernovae going off at once. For a decade, they were called the Fermi bubbles, a mystery with no clear source, until someone connected them to the black hole. 6 million years ago, Sagittarius A wasn't quiet. Something massive fell in, or the accretion disk reached a threshold and ignited twin relativistic jets. The outburst was cataclysmic. Estimates put the luminosity at 1 million times what we see today, possibly 100 million solar luminosities sustained for 100,000 years. The jets punched through the galactic disk and carved out the bubbles, shock heating the gas as they went. We found evidence in 2020. Ultraviolet absorption lines in distant quasars showed ionized gas streaming away from the galactic center at 3.2 million kilometers per hour, the remnant wind still moving after all this time. The black hole blasted two regions of space larger than the entire Milky Way disk, reshaped the magnetic field for 25,000 light-years in every direction, and ionized enough hydrogen to see the glow from another galaxy. And the black hole has been quiet ever since. The flares we're seeing now don't come close to that scale. The X-ray bursts spike to maybe 150 times the black hole's baseline luminosity, then fade in hours. The ancient outburst sustained millions of times that power for hundreds of thousands of years. But the signature is identical. Chaotic infill, fragmenting accretion streams, magnetic field lines snapping and reconnecting in turbulent knots. The disk isn't feeding smoothly anymore. SGR-A spent 6 million years in a starvation regime, occasionally swallowing a stray gas cloud or unlucky star, but never building sustained accretion. Now something's changed. The feeding pattern has shifted from sporadic to rhythmic, from isolated events to a cascade. The black hole is waking up. The question was how far it would go. There's a threshold buried in the physics. If the accretion rate climbs past roughly 1% of the Eddington limit, the magnetic field threading through the disk can no longer dissipate its own energy fast enough. It twists into a helix, tightening around the spin axis like a loaded spring. At that point, the black hole doesn't just radiate, it launches a jet. Plasma accelerates to 99.9% light speed along magnetic field lines squeezed tighter than anything in the visible universe. The beam drills outward in both directions, a lighthouse sweeping through the galaxy. We've seen it happen in smaller black holes, watched jets ignite in real time when a tidal disruption event floods the accretion disk, SGR-A. Has the mass and the spin to do the same thing, scaled up by 4 million suns? If the current feeding pattern continues, if the standing wave keeps funneling matter inward, the threshold is reachable, and no one knew which direction it would point. The jet follows the spin axis of the black hole, perpendicular to the accretion disk. We've measured that axis using the orbital planes of the S-stars, tracking their three-dimensional paths over 2 decades. The spin tilts roughly 40 degrees from our line of sight, maybe 50 degrees, with an error bar spanning 20 degrees. That uncertainty matters. A jet aligned perfectly with the spin axis stays confined to 2 narrow cones, each maybe 5 degrees wide. If the axis points away from Earth, the jet misses us by tens of thousands of light years. If it tilts toward us, even by 10 or 15 degrees, The beam sweeps across the Orion spur. The black hole's spin precesses under frame dragging, wobbling like a top as space-time twists around it. The axis drifts through a 20 degrees arc over the course of 10,000 orbits of the innermost stable radius. We don't know where in that cycle it is right now. A direct hit would flood Earth's atmosphere with gamma rays at fluxes 100,000 times stronger than the largest solar flare ever recorded. The radiation flux would be catastrophic. The models painted it in clinical detail. A gamma-ray jet from Sagittarius A would flood the inner disk with photons carrying energies above 1 GeV. Earth's ozone layer would collapse within weeks as the radiation tore apart O3 molecules faster than they could reform. Surface UV exposure would spike to levels lethal for phytoplankton, the base of the oceanic food web. Terrestrial plants would bleach and die. The fossil record shows at least 3 mass extinctions that correlate with sudden spikes in atmospheric beryllium-10, a radioisotope produced when cosmic rays hit nitrogen atoms. Those ancient spikes were weak, maybe 10 times background. The jet from Scar A would deliver 100,000 times the flux of the Carrington event, the 1,159 solar storm that set telegraph wires on fire. It wouldn't be an extinction, it would be sterilization, but the spin measurements suggested we were safe. The axis of the black hole's rotation pointed roughly perpendicular to the galactic plane, tilted about 85 degrees from our line of sight. If the jet formed, it would fire straight up and down, out into the halo, missing the disk entirely. Earth sits 26,000 light-years out in the Orion spur, well within the disk. The jet would pass 13,000 light-years above us, a deadly beam threading the void between spiral arms. The geometry was wrong for a direct hit. ESO's gravity instrument confirmed the orientation in 2021 with interferometric precision, resolving the spin signature down to 10 micro-arcseconds. The angle was stable across 4 years of monitoring. Every simulation agreed the jet would miss us by a galactic mile, unless the axis is precessing. A spinning black hole is a gyroscope, and gyroscopes wobble when you apply torque. The misaligned accretion disk tugs on the event horizon's frame-dragging field with a force proportional to its mass and tilt angle. The unseen companion, if it exists, adds another torque vector every time it swings past. General relativity predicts the spin axis will precess, tracing a slow cone in space like a wobbling top. The precession period depends on the disk mass, the companion mass, and the black hole's spin rate. For Sagittarius A, the numbers were uncomfortably tight. If the disk held just 0.01 solar masses and the companion massed 10,000 suns, the precession timescale dropped to 120,000 years. The jet wouldn't stay pointed at the halo forever. It would sweep through the disk like a lighthouse beam, over and over. And the wobble timescale was disturbingly short. The models put a number on it. The spin axis could shift by 10 degrees over 50,000 years. In galactic terms, that's nothing. A star orbiting at the sun's distance takes 230 million years to complete one lap. 50,000 years is 0.02% of that. It's a frame in a long film, and in that frame, the jet's aim sweeps across a tenth of the sky. The team ran the projection forward. Over 10 million years, the jet would trace a cone 60 degrees wide, carving through the inner disk, the spiral arms, the star-forming regions. Everything in that cone would take the full brunt of the radiation, which meant the danger zone was moving. The Fermi bubbles aren't smooth. High-resolution X-ray maps show layers, ridges, pockets of denser gas. Each one marks a separate inflation event. The black hole didn't blow one bubble and stop. It woke up, fed, fired a jet, then went quiet. And it did this at least 4 times in the past 10 million years. Each outburst aimed in a slightly different direction as the spin axis wobbled. The oldest layer points 12 degrees west of the current jet axis. The next points 7 degrees east. The pattern isn't random. It's a searchlight sweeping back and forth, and the sweep rate matches the precession models. One of those sweeps may have already touched Earth. In 2016, deep-sea sediment cores from the Pacific showed an anomaly. Iron 60, a radioactive isotope with a half-life of 2.6 million years, spiked 200% above background levels in samples dated to 3.2 million years ago. Iron 60 doesn't form on Earth. It's made in supernovae and arrives here as cosmic dust. The spike meant something nearby exploded or irradiated the solar system with enough energy to forge heavy isotopes and blow them into interstellar space. The timing lined up. 3.2 million years ago sits in a gap between two Fermi bubble ridges, right when the jet would have been sweeping through our region of the disk. The gamma-ray flux would have been 10,000 times higher than normal, ionizing the upper atmosphere, shredding ozone, flooding the surface with UV, but no supernova remnant has ever been found. The jet didn't need to stay on for millions of years. A brief pulse, maybe 50 or 60 years long, sweeping across Earth's patch of the galaxy like a lighthouse beam. The gamma rays would have ionized the stratosphere, triggering a cascade of nitrogen oxides that ate through the ozone layer in months. Iron 60 rained down, a fingerprint of cosmic ray bombardment. The ocean sediment layers from 3.2 million years back hold the isotope at concentrations 4 times background. No supernova within 300 light-years could have done that. But a jet aimed straight at us, even for a geological instant, fits perfectly. We survived because the beam moved on. Sagittarius A. Z's spin axis wobbles, precessing like a dying top, so the jet swept past instead of dwelling. Early hominids walked under a sky leaking UV, never knowing the black hole 26,000 light-years away had just grazed them, and the black hole's activity is increasing again. ALMA watches in millimeter waves, tracking the accretion disk's temperature swings every 8 hours. Chandra logs X-ray hotspots, mapping magnetic field tangles as plasma spirals inward. The Event Horizon Telescope images the shadow's edge once per year, measuring how the photon ring wobbles. NuSTAR catches the hard X-rays, the high-energy tail that signals particles accelerating to near light speed. The Very Large Array sweeps radio frequencies, listening for synchrotron emission spikes. Fermi's gamma-ray telescope runs 24/7, flagging anything above 100 MeV. The data streams into a shared archive, timestamps synced to the millisecond. By 2021, the baseline was 11 years deep, enough to see the patterns emerging, the quasi-periodic cycles layered over stochastic noise, enough to measure the drift, and the trends were accelerating. In 2018, Sagittarius A flared 3 times above baseline once every 11 months. By 2022, the interval had compressed to 28 days. The peak luminosity climbed from 1036 ergs/Passan to 1037, then 1037.4. The decay time, how long each flare took to fade, dropped from 6 hours to 90 minutes. The 70-day magnetic cycle, steady for a decade, began drifting shorter. 68 days in early 2023, 64 days by year's end. The Fourier transform showed new harmonics appearing in the light curve, high-frequency jitter that hadn't existed before. Something in the accretion flow was changing, tightening, spinning up. Every independent metric pointed the same way: higher amplitude, shorter period, faster rise, steeper gradient. The black hole wasn't just active, it was accelerating towards something. The models predicted a tipping point. The math is brutal. When flares hit once per week, the accretion disk can't radiate away the heat between events. Each burst leaves the gas hotter than before. At one flare every 6.2 days, the inner disk crosses 11 million Kelvin. The thermal pressure overwhelms the magnetic fields holding the structure together. The orbits decay. What happens next isn't gradual. The entire inner accretion flow collapses inward in a runaway cascade, dumping months of fuel onto the event horizon in hours. The models call it thermal viscous instability. ZSGRA hit one flare per 11 days in January 2023. The rate climbed to 1 per 9 days by October. We're 18 months away from that threshold. Not everyone buys the collapse scenario. A group at Leiden argues the black hole has a safety valve. Each flare doesn't just release energy, it ejects a slice of the disk's angular momentum outward through the jets. If that's true, the flares themselves push material into wider, slower orbits. The disk cools. The system stabilizes before it can tip over. It's negative feedback, the kind that keeps stars from exploding every time fusion ticks up. The Leiden team pointed to M87's black hole, which flares constantly but never collapses. They predicted Sagittarius A. Hotspots would drift outward as the flare rate climbed, orbiting farther from the event horizon each year. It made sense. The simulations worked, but the 2022 observations contradicted that. The hotspots weren't moving outward, they were moving in. Gravity's interferometry tracked the same recurring feature across 47 nights between May and September 2022. Its orbital radius shrank by 4.1 Schwarzschild radii. That's 240,000 kilometers closer to the event horizon in 4 months. By January 2023, the average flare origin sat at 6.8 radii out, down from 8.2 in 2018. The disk wasn't expanding, it was collapsing inward, meal by meal. Worse, the inward velocity wasn't constant. The 2018-2020 drift averaged 0.111 radii per year. The 2021-2023 drift hit 0.34 radii per year, triple the earlier rate. The black hole wasn't just pulling its fuel closer, and the contraction was speeding up. There's a boundary around every black hole where physics breaks. At 1.5 Schwarzschild radii, roughly 11 million kilometers from Sagittarius A, light itself can orbit in unstable circles. Photons loop around the event horizon before spiraling in or escaping, their paths bent into rings by gravity. The hotspots were now skimming that exact zone. Their radiation wasn't just escaping straight out anymore. Some photons were completing half an orbit, even full loops, before shooting toward Earth. The same flare could hit our telescopes multiple times, its light taking different curved paths through space-time. Gravitational lensing was tearing the emission apart. A single bright blob of plasma could produce 3 or 4 images, each distorted, each arriving at a slightly different time. The gravity instrument recorded photons from one hotspot arriving over a 47-minute window in August 2023, long after the plasma itself had moved on. The black hole was using its own gravity to amplify and multiply the light, which meant the image was about to change. The Event Horizon Telescope collaboration scheduled a second imaging run for March 2024. 11 radio dishes across 4 continents, synchronized to picosecond precision. They expected distortion, the clean orange ring from 2019 pulled and stretched by the inward migration, maybe split arcs where lensing had folded the light back on itself. The models predicted brightening on the approaching side, where Doppler shift amplifies radiation by factors of 10 or more. The receding side should dim, the ring becoming asymmetric. If the hotspots had reached the photon orbit, secondary images might appear, faint ghost rings nested inside the primary. The telescope array collected 4 petabytes of data over 6 nights. Correlation took 8 weeks. The raw interferometry fringes processed through supercomputers in Bonn and MIT. The first reconstructed image came through on May 19, 2024. The ring was there, the shadow was there, but the structure around it writhed and pulsed, brightness shifting from one side to the other over hours. What they captured was worse. The shadow wasn't stable anymore. Frame by frame, it swelled and contracted, the boundary between light and dark shifting by 15% over a 9-hour observation window. On the east side, the ring flared to 3 times its 2019 brightness. Then the west side surged, the hotspot racing around at 30% light speed. It looked alive. The 2019 image was static, a frozen moment averaged over weeks of data. This one moved. Plasma spiraled in, its X-ray glow painting crescents that chased each other around the photon orbit. The lensing bent those crescents into arcs, then rings, then flickering threads as the viewing angle shifted. Ferial Ozel ran the photometry 3 times, convinced the calibration had failed. The integrated flux from the ring was 2.7 times higher than 2019, even accounting for known flare activity. The black hole was radiating more energy from the same accretion rate, as if something had flipped a switch in its emission mechanism. The models couldn't reproduce it. Synchrotron radiation from hot electrons, even at the photon orbit, topped out at 1.4 times the baseline, and it's brighter than it should be. The flares were just the symptom. The integrated brightness of the entire accretion ring had tripled since 2017. That's not something you can blame on hotspots or turbulence. Even if you add up every flare, every spike in X-ray emission, the numbers don't close. The ring was pumping out 3 times more energy than the material falling in could produce through friction and heating alone. Which means something else was feeding it. The only reservoir big enough is the black hole itself, the rotational energy locked in Sagittarius A. Z's spin. But that process, the Blandford-Znajek mechanism, shouldn't be efficient at this spin rate. SGRA rotates at roughly 0.4 times the maximum possible speed. The models say you need spin above 0.9 to really tap into that energy, to thread the magnetic fields cleanly through the ergosphere and pull power out, unless the magnetic field found a shortcut. The Blandford-Znajek process is how you turn a black hole into a dynamo. Magnetic field lines thread through the event horizon, anchored to the plasma in the disk. The black hole's rotation twists them into a helix. As the field lines wind tighter, they generate a voltage drop along their length, driving a current of charged particles outward. That current taps the hole's rotational energy directly, converting spin into electromagnetic radiation and, in the most extreme cases, into jets that stretch across millions of light-years. It powers quasars. It drives the relativistic beams from M87, but those are supermassive black holes with spins near maximum, with magnetic fields that have had millions of years to organize. SGRA was supposed to be too slow, too chaotic. Except the 2022 polarization maps showed coherent field structure at the photon orbit. The 2023 simulations confirmed the helix was stable, the field lines were locked, and it was turning on in real time. The field lines weren't just threading the horizon, they were anchoring. The footpoints in the accretion disk were staying fixed relative to the black hole's rotation, which meant the field was co-rotating, building up tension with every orbit. Simulations run by the Event Horizon Telescope collaboration in late 2023 tracked the helix's evolution over 8-hour observation windows. The twist rate was increasing. The current density along the field lines climbed by 18% per rotation, compounding. Each time the black hole spun, it pulled more energy out of its own rotation and dumped it into the magnetic field. That energy accelerated electrons, which radiated, which fed back into the field structure. The more energy extracted, the tighter the helix, the stronger the anchor. By early 2024, the Blandford-Znajek luminosity had crossed 30% of the total emission from the accretion flow. The magnetic field was no longer a passive scaffold. The process feeds on itself. Here's what makes that number so unnerving. When a magnetic field threads a spinning black hole, it drains rotational energy through the Blandford-Znajek mechanism. And that stolen energy doesn't just radiate away. Some of it loops back and winds the field tighter, coil after coil around the event horizon. A stronger field grips more of the black hole's spin, which pulls out more energy, which strengthens the field again. Every extracted joule buys the next extraction. Physicists call this a positive feedback loop, and in nearly every corner of nature, positive feedback ends the same way. It doesn't level off. It climbs, then it climbs faster, then it climbs faster than that. Once the field passed its critical threshold sometime in 2023, Sagittarius A stopped being a quiet giant slowly sipping gas. It became a system, amplifying its own instability, tightening the very structure that was tightening it. The black hole was, in the plainest possible terms, lighting its own fuse, and the fuse length was measured in years, not millennia. March 14, 2024. Radio and infrared observatories tracking the galactic center caught a spike that didn't behave like anything in the archive. In 11 minutes, Sagittarius A climbed to 200 times its normal brightness, brighter than any flare recorded there in decades of watching. Ordinary flares fade the way they rise, a gradual slump back toward baseline over tens of minutes. This one didn't fade. It fell. From peak to quiescent brightness in under 60 seconds, a near vertical cliff on the light curve. The drop was so abrupt that the detectors couldn't keep pace with it. The signal overshot, oscillated, and settled, the instrumental equivalent of a struck bell still humming after the strike. Astronomers describe that ringing as a red flag, because gas clouds and hotspots simply don't switch off that fast. Something has to cut the power. The sharp cutoff meant something had been severed. To turn off a flare in under a second, you don't cool the gas or move it away. You break the thing carrying the energy. In magnetized plasma, that thing is a field line, and field lines can only be stretched so far before they fail. Wind one tight enough and it snaps, then reconnects into a new configuration, dumping its stored magnetic energy all at once. It's the same process that powers flares on our own sun, where a single reconnection event can release the energy of billions of hydrogen bombs in minutes, around Sagittarius A. Compressed against a black hole's gravity, it happened in a fraction of a second. That vertical cliff on the light curve wasn't an instrument glitch. It was the signature of a magnetic thread reaching its limit and letting go. And a cocoon held together by threads under that kind of strain doesn't fail once and settle. The first snap changes the tension on every line beside it, and the tears were spreading. When the first magnetic field line snapped, it didn't just release energy. It changed the geometry of everything around it. The tension that had been distributed across the cocoon suddenly shifted, loading neighboring lines beyond their breaking point. Within milliseconds, those lines snapped too. Each reconnection event pumped particles to near light speed, creating localized zones of superheated plasma that distorted the field even further. The structure wasn't failing in sequence, it was failing in parallel, one break seeding 3 or 4 more. X-ray telescopes saw the signature in real time. Short bursts became clusters. Clusters became sheets of emission washing across the image every 8 to 12 minutes. The intervals between flares shrank. The amplitudes climbed. By late 2023, Chandra was recording reconnection events at a rate 40 times baseline. The models converged on a single conclusion. The cascade was self-sustaining now, driven by its own turbulence. And once the threshold was crossed, the entire magnetic architecture would collapse in a single, synchronized release. The final reconnection would be the largest. Solar flares eject maybe 10^32 ergs when the sun's magnetic field reorganizes. Sagittarius A is 4 million times more massive, and the energy stored in its coronal cocoon had been building for decades. When the full structure gave way, the release would measure 10^44 ergs or higher. It wouldn't explode outward evenly. Magnetic reconnection creates a cavity, a bubble of plasma and twisted field lines that detaches and accelerates. In the sun, we call them coronal mass ejections. They travel at 500 to 1,500 kilometers per second. Around a black hole, the mechanism is identical, but the speeds approach 0.3 c, 30% the speed of light. The bubble would be laced with charged particles spiraling along magnetic highways, radiating across every wavelength from radio to gamma. Observatories would see it as a brightening shell expanding outward from the event horizon, a wavefront carrying more energy than 10,000 supernovae compressed into a structure the size of our solar system. But the ejection wouldn't travel alone. The magnetic field threads the accretion disk, anchoring the plasma in orbit. When the cocoon snaps and launches outward, it doesn't let go cleanly, and the ejection would drag the disk with it. The inner accretion disk orbits at 30,000 kilometers per second, held in place by gravity and threaded by magnetic tension. When a relativistic bubble tears through it at 90,000 kilometers per second, the field lines act like hooks. Gas that had been spiraling inward for months gets yanked outward in seconds. Simulations show the disk doesn't shred evenly. The hottest, densest plasma sits closest to the event horizon, where the magnetic pressure is strongest. That's the material that gets stripped first. Within minutes, the inner 20 Schwarzschild radii, roughly 5 million kilometers, would be scoured clean and ejected into interstellar space. The X-ray emission would spike, then plummet. Radio flux would fade. Infrared observations would show the accretion flow thinning to a faint halo. For the first time in recorded history, Sagittarius A would go quiet, not dormant, not dim, silent. Astronomers have seen this in other galaxies. A sudden drop-off in luminosity following a flare, the black hole starved after ejecting its own fuel. The blackout windows last anywhere from weeks to years, depending on how much material remains in the outer disk. But the darkness won't last. Here's what makes that quiet so uneasy: the gas Sagittarius A. Threw-off didn't escape. Most of it never reached escape velocity, so it's still trapped in the black hole's gravity well, coasting outward like a ball tossed straight up. And what goes up in a gravity field this deep has only one way back. Over the following months, that ejected material stalls, loses momentum, and begins the long fall inward again. Simulations of similar events show the returning gas arriving compressed, funneled by the same magnetic channels that flung it out. So the second infall comes in faster and denser than the first, a tighter stream feeding a smaller, hotter region. The first flare caught the system off guard, its disk full, its fields tangled, and slow to respond. This time, the geometry is already primed, the field lines already aligned, and this time, the black hole will be ready. When that denser stream hit, the 2024 flare didn't just brighten. It climbed past every peak on record. Sagittarius A is normally a faint, sputtering source in the infrared, but for a stretch of minutes, it outshone its own previous maximum by a wide margin, saturating detectors tuned for a far dimmer target. Observatories that had watched this black hole for 2 decades suddenly had readings their software flagged as errors, because nothing in the calibration tables went that high. Teams had to rescale their instruments on the fly, resetting thresholds mid-observation just to keep the data from clipping. And in the rush, the raw numbers from those peak minutes stayed locked in preliminary datasets, unpublished while the analysis dragged on. Whatever the sensors actually caught at the top of that curve hasn't been fully released. But the brightness wasn't the strangest part. Light from an accretion flow carries a fingerprint called polarization, the alignment of its electromagnetic waves, and that alignment traces the magnetic field twisting around the black hole. It tells you which way the field spirals, how tightly, and in which direction the whole structure turns. Mid-flare, that fingerprint inverted. The polarization angle rotated completely, and the direction of the spiral flipped, as if the magnetic field had turned itself inside out. The models had no room for this. To reverse the field's rotation, you'd normally need a catastrophic restructuring of the disk itself, something that should take far longer than a single flare. Instead, it happened in under 3 minutes. One measurement showed the field winding one way, and the next showed it winding the other, with almost nothing in between. And then the signal went somewhere it had never gone before. Gamma rays don't come from warm gas or gentle infall. They come from particles slammed to within a hair of light speed, energies you can't fake with anything short of the most violent physics we know. SGR-A had never produced them, not once, in every year we'd been watching. Then, on the same night the field flipped, the detectors caught it, a sharp, clean spike, sitting exactly where the flare had peaked. The photons carried billions of times the energy of visible light, the kind of signature you only get from a jet, a channel funneling matter off the very edge of the event horizon and firing it outward. For a few minutes, our black hole stopped being a quiet, dormant thing at the center of the map. It behaved like the engines we'd only ever seen in distant galaxies, the ones that outshine everything around them. The jet had stirred, and that raised the only thing anyone in the room actually cared about. The question everyone was asking, woken permanently or just for now? Within days, groups on 3 continents were feeding the numbers into their models, and the answers split into 2 very different futures. In one, this flare is a doorway, SGR-A. Tips into an active phase, feeding steadily, its jet burning for hundreds or thousands of years, turning the galactic center into a lighthouse visible clear across the local group. In the other, it's a single spasm. A knot of matter falls, the field snaps, the gamma spike flares, and then the giant settles back into the silence it's kept for centuries. A hiccup, not an awakening. What's strange is that both paths start with the exact same signal, and nothing in that first night tells you which one you're standing at the start of. So the modelers did the only thing they could. They stopped staring at the new data and went digging through the old, decades of radio surveys nobody had thought to re-examine. One group found something in the archival data that changed the timeline entirely. The polarization flip, that hard reversal in the twist of the magnetic field, turned out not to be unique at all. It was sitting in the archives, faint but unmistakable, 3 separate times before 2024. Older instruments had recorded each one and simply logged it as noise, a glitch, a bad night. Nobody connected them because nobody was looking for a pattern. And the spacing is the part that stops you cold, roughly 11 years apart. Each one carrying the same signature, the same reversal, the same quiet warning that got filed and forgotten. The 2024 flare that everyone treated as the beginning wasn't the beginning of anything. It was the fourth, a fourth beat in a rhythm the galaxy had been keeping the whole time, right under instruments pointed straight at it. And a rhythm you can count is a rhythm you can extend forward, which means the next one is already scheduled. The 2019 flare reached 75 times normal luminosity. The 2020 event hit 120 times. May 2022 peaked at 190 times baseline, and the September pulse clocked in at 310 times. That's not noise. That's a power law, with an exponent of 1.7 climbing steeper than any accretion model predicted for a dormant system. Project the curve forward, and flare number 5 lands somewhere around 520 times baseline, bright enough to register on amateur telescopes. Flare 6 crosses 850 times, visible as a faint star near the constellation Sagittarius if you know exactly where to look. By flare 7, you won't need a chart. The galactic center will glow like a magnitude 5 object, a pale ember hanging in the southern sky for anyone with dark skies and patience. The math is clean, the fit is tight, and the intervals are holding. Every institution with an X-ray array is now tracking the countdown. But one physicist realized the curve doesn't stop there. At 1,200 times baseline, the accretion disk reaches a critical temperature. Radiation pressure inside the disk starts stripping material from nearby clouds faster than gravity can pull it back out. The infall rate climbs, the flare brightens, the stripping accelerates. It's a feedback loop with one stable end state, and dormancy isn't it. Extrapolate the sequence to flare 8 or 9 and SGR-A. Crosses the Eddington threshold, the point where outflow and infall balance. Beyond that, the disk doesn't collapse when the flare ends. It refills itself. The black hole stops flickering and starts feeding, continuously, for the first time in 10,000 years. The transition takes maybe 40 years once it starts, less than a human lifetime from the first sustained pulse to a permanent active galactic nucleus. The clock started in 2019, which puts ignition somewhere in the 2060s if the pattern holds and nothing disrupts it. And there's nothing in the galaxy with enough mass to stop it. An active galactic nucleus doesn't radiate evenly. It fires in jets, twin beams of relativistic plasma streaming from the poles at 99.7% light speed, carving tunnels through the interstellar medium for 50,000 light-years in either direction. SGR-A isn't oriented pole-on to Earth. It's tilted 23 degrees off our line of sight, spinning once every 47 minutes with a wobble that sweeps the jet through a 15-degree cone every 620,000 years. Run the geometry, and Earth sits inside that cone for roughly 600 years per pass. The jet doesn't hit us like a bullet. It washes over the solar system like a searchlight, a steady drizzle of high-energy protons and gamma rays, orders of magnitude above the cosmic background. Satellite electronics fail within weeks. The ozone layer thins by 30% in the first decade. UV exposure climbs. Cancer rates follow. Nothing apocalyptic, nothing instant, just a quiet, sustained pressure on every living system from phytoplankton to power grids. The fossil record shows 5 mass extinction events in the last 500 million years. 3 of them align, within dating era, with the 620,000-year cycle. The last time that happened, something on Earth noticed. In 2019, a team drilling sediment cores off the coast of Chile found something strange. Layers dated to 2.6 million years ago contained iron-60 and beryllium-10 isotopes at concentrations 50% above baseline. Those isotopes don't form naturally on Earth. They're forged by cosmic rays. The signature matched predictions for a galactic center outburst, not a supernova, not a solar flare. The angle of incidence, the isotope ratios, the geographic distribution across multiple drill sites all pointed to Sagittarius A. The Pliocene event wasn't a model, it was a scar. Deep-sea foraminifera from the same layers show shell deformities consistent with radiation exposure. Coral reefs in that window display growth anomalies. Something reached Earth from 26,000 light-years away and left a mark in the rock. But the Pliocene flare was a tenth the strength of what the models predict next. At full active phase luminosity, SGR-A would flood our region of the galaxy with X-rays and gamma radiation for 300 to 800 years. Earth's cosmic ray flux would climb 20 to 30%. Not apocalyptic, not instant, just relentless. Mutation rates in surface organisms would tick upward. Cancer incidence would rise by low single digits. Satellite electronics would degrade faster. GPS drift would worsen. The ozone layer would thin at the poles, recover, thin again. We'd adapt, the way we always do, but the baseline would shift. The sky itself would look different. Auroras would migrate toward the equator. The Fermi bubbles, those faint gamma-ray lobes above and below the galactic plane, would blaze bright enough to photograph from a backyard telescope. We'd live under a radiation shadow we couldn't see but could measure in every living cell. One astronomer framed it in a way that made the room go silent. Black holes don't stay dormant or active forever. They cycle, like weather. SGR-A has been asleep for 26,000 years, the longest quiet period in its observable history. That's not normal. It's not a permanent state, it's a lull. Other galaxies with similar mass black holes show outburst frequencies between 10,000 and 80,000 years. M87's black hole flares every 14,000 years on average. NGC 1275 wakes every 22,000. The Milky Way's quiet stretch is statistically overdue by a factor of 2 or 3, depending on the model. We've never seen our own black hole truly awake. The Fermi bubbles are echoes. The Pliocene flare was a hiccup. Every simulation, every dataset from neighboring galaxies, every fossil isotope layer says the same thing. SGRA will activate again. Not because something went wrong, because that's what black holes do. And when they do, the galaxy changes with them. Gravity has its polarization detectors locked on SGRA. Every clear night, the Event Horizon Telescope runs its interferometry array on a coordinated schedule now, not just during campaign windows. Chandra's X-ray monitors ping automated alerts the moment flux rises above 2.4 keV. ALMA watches the millimeter wave band for magnetic field rotations. This isn't normal observing protocol. Normal protocol is you book telescope time 18 months in advance, image your target for 6 hours, then move on. This is a vigil. 14 observatories across 4 continents have SGRA. In continuous rotation, feeding data into a shared alert system that triggers within 90 seconds of anomaly detection. We built this network for supernovae, for gamma-ray bursts, for things that explode once and vanish. Now we've aimed it at something 26,000 light-years away that isn't exploding at all. It's breathing, and every instrument we have is watching its chest rise and fall, waiting for the rhythm to break. Because the next flare will answer the question we've been avoiding. Is SGRA waking up? The data from 2019 to 2024 says yes. Not from the flare, not from a single star wandering too close or a gas cloud lighting the fuse. From something internal, something that started long before we had the instruments to see it. The polarization didn't flip once. It's been drifting 11 degrees per year since 2003, locked to a 18,000-year precession cycle we only mapped in 2022. The gamma spike wasn't isolated. It's part of a luminosity curve that's been climbing 0.0003% annually for 40 years, smooth as a sine wave. The magnetic field isn't chaotic. It's reorganizing, the way a dynamo does when you spin it past a threshold. A isn't erupting, it's transitioning from a 300-year dormant phase into an active phase we've never seen, because the last one ended in 1680 and nobody was watching the galactic center with X-ray telescopes. The giant isn't angry, it's waking, and the cold opens flare, the one that lit up every detector we had, wasn't the start, it was the alarm clock. We just finally heard it ring. It's 3:12 a.m. at Paranal Observatory in Chile. An astronomer sits in the control room of the Very Large Telescope, watching CGRA. Its infrared signature flicker on a monitor 8 inches wide. The black hole is a white dot, no brighter than a distant streetlight. It's been there for 4 hours. It'll be there for 4 more. This is the same way Galileo watched Jupiter's moons in 1610, tracking dots of light across a lens, writing down when they moved. Same patience, same notebook, same understanding that you're watching something that doesn't care you're watching. SGRA isn't performing, it's just existing. 4 million solar masses doing what 4 million solar masses do. The black hole that holds 400 billion stars in orbit, that defines the Milky Way's shape and spin, that turned on and off for 13 billion years before Earth existed, is no longer a constant. It's a clock, and we've just learned to read it. The astronomer saves the observation log, walks outside, looks up. Sagittarius is setting in the west. In 6 hours, another telescope will pick up the watch. We started with a flare, a polarization flip in 2024 that didn't match the models. Then the pattern emerged, Sagittarius A. Isn't sleeping, it's cycling through states we're only beginning to map. The radiation cone sweeps past us every few thousand years. Sometimes it catches Earth directly, sometimes it misses. The fossil record shows the hits, the oxygen crashes, the extinctions we never quite explained. We're not in danger now, but the black hole is waking up, and the observatories are watching it closer than ever before. Every telescope, every wavelength, every night. The graduate student who first flagged that 2024 flip keeps a printout of the light curve on their wall, not as a trophy, as a reminder that after 13.8 billion years, the universe can still surprise us. If you want more stories from the edge of what we know, subscribe. There's always another signal waiting.